the place where we let curiosity wander without a timer and give big questions the time they deserve. This isn't the sort of space for rushing through bullet points or hurrying to the end. Here, the goal is to slow things down enough that we can actually think about the strange, fascinating, and sometimes unsettling things our universe has been hiding in plain sight. Tonight, the idea we're exploring is one that has been quietly sitting in the background of astronomy and science fiction for years, but rarely given the kind of attention it deserves. It's the thought that Earth, the place where you and I are sitting right now, the place that feels permanent and singular, might not be all that special after all. Not in the sense of beauty or meaning, but in the sense of being alone. That maybe there have been many other worlds like ours, full of oceans and land and atmosphere, maybe even life, and that most of them didn't make it. It's a strange and slightly uncomfortable concept, isn't it? We like to think of our planet as the lucky winner, the one place in a hostile universe where everything clicked into place. But what if the truth is more complicated? What if, instead of being 1 in a billion, Earth is just one of the few survivors in a universe littered with failed attempts? That out there, scattered across light years, are the remains of worlds that tried to do what ours has done and simply couldn't hold on. Before we go further, I want you to take a moment to think about where you are right now. Not just the city or country, but the exact little corner of the planet you're in. Are you indoors with the hum of appliances around you, or outside where you can hear the wind moving through leaves or the distant sound of traffic? Is it day where you are, with sunlight spilling through windows or stretching shadows across the ground? Or is it night, with the sky dark above you, maybe hiding stars behind clouds or bright with city lights? Picture your location in your mind for just a moment, and remember that all of this, the place you are in, the air you're breathing, the ground under your feet, is tied to this one world. This thin shell of rock, water and atmosphere is the only place we've ever known, and every second of your life has happened here. That thought alone can be grounding, but it can also open the door to a different perspective. If Earth is the only place we've experienced, it's easy to assume it's rare or unique by default. We don't have a personal frame of reference for other planets. We can look through telescopes, send out spacecraft, even detect exoplanets orbiting distant stars. But none of that is the same as standing somewhere else and breathing a different sky. That's why the idea of other Earth-like worlds feels abstract. We know the numbers suggest they're out there. Thousands already found, probably billions more waiting. But they're so far away that they might as well be myths. And when something feels like a myth, we have a habit of simplifying it. We imagine 2 categories: the dead, airless rocks, and the lucky gems like Earth. But the more we learn about the universe, the more it seems like there's a much bigger middle ground. Worlds that had promise, worlds that might have started something, worlds that maybe even reached a point of thriving before they didn't. This is where the thought starts to take shape. If the conditions for life aren't impossibly rare, then life itself might not be either. And if life can start in more than one place, then logically, some of those places might not have survived the long journey from microbes to complex ecosystems. There's no law that says once a planet gets life, it keeps it forever. Stars change, atmospheres leak, temperatures swing, cosmic accidents happen, and life, for all its adaptability, has limits. When those limits are crossed, the chapter for that world closes. It becomes one more name in what we could call the universe's quiet list of failed experiments. Think about our own solar system for a second. We already have examples close to home. Mars might have once had flowing rivers and a thicker atmosphere. Venus might have once had oceans before it became the hottest surface in the solar system. Even moons like Europa and Enceladus have underground oceans today, hinting that they might have had or could have life in some form. These aren't purely dead rocks from the start. They're candidates for what might be called almost worlds, and that's just in our small corner of the galaxy. If we can find several possibilities within reach of a single space probe, imagine how many more there might be across the Milky Way alone. It's easy to feel like this is a depressing line of thought, but it doesn't have to be. There's a different kind of wonder in it. It means that life is not only possible in many places, but that it has tried again and again. That the universe might be full of stories we'll never hear. Civilizations that rose and fell, ecosystems that bloomed and vanished, seas that once had waves and now are just dry basins under alien suns. And somewhere in the middle of all that, Earth has made it this far. Not because it was guaranteed, but because a lot of conditions happened to line up, and so far, we've avoided the kind of event that could end the whole thing. Before we go too deep into distant planets and their silent histories, I want to bring this back to you for a moment. I'm curious, if you could stand on the surface of one of these other worlds, even knowing it's lifeless now, would you want to? Would you want to see the traces of what was there before? Or would you prefer to keep those places in the realm of mystery? It's the sort of question that doesn't have a right answer, but thinking about it might help us understand our own place here a little better. If you've made it this far, listening to me lead you into this thought, I'd like to ask for a small favour. If you're enjoying this slow, careful way of exploring an idea, one that doesn't rush to the conclusion, but lets us sit with the questions, consider liking this video or subscribing. It helps keep this small space alive so more people can join in these quiet explorations. So here we are, standing on our living planet, surrounded by the possibility that it's just one survivor in a universe of lost worlds. And the only way to really start understanding that is to look outward. Beyond the blue sky we know so well, into the places that may have once been alive and aren't anymore. That's where we're heading next. When we look at Earth from the surface, it's easy to forget how small and fragile it is. Our daily view is up close. Streets, buildings, trees, the sky overhead. Even the horizon feels vast until you remember that, compared to the scale of space, it's barely a scratch on the surface of a sphere less than 13,000 kilometers across. But step far enough away, and the picture changes. From the moon, Earth looks like a bright round jewel against the black. From the outer planets, it shrinks to a pale dot that you could block out with a fingertip. And from interstellar distances, even that dot disappears. The entire planet, every person you've ever known, every event in human history, all of it fits into a point so small you'd lose it in the static. That perspective has a way of softening the certainty that we're central to anything. It's not meant to make us feel insignificant, though it can, but rather to remind us that we're part of a much larger story. And in that story, Earth may not be a singular main character. It could be just one among countless planets, each with its own brief chapter in the universe's history. When you think about it that way, the idea that we're the only successful one starts to feel less like a fact and more like a gamble we happen to win, for now. Astronomers have been working for decades to get a clearer picture of how common Earth-like planets are. For most of human history, the question wasn't even a scientific one. We could see other planets in our solar system, but beyond that, stars were just points of light with no visible worlds of their own. The first confirmed detection of an exoplanet, a planet orbiting a star outside our solar system, didn't come until the early 1990s, and since then, the number has grown into the thousands, with new ones found almost every month. Many of them are nothing like Earth, gas giants, scorched lava worlds, frozen orbs, but some are eerily familiar in size and orbit. Some even sit in what's called the habitable zone, the range where liquid water could exist. The phrase habitable zone is misleading though. It doesn't mean the planet is actually habitable, just that it could be, if other conditions line up. A world could be the right distance from its star but still lack an atmosphere, or have one that's toxic. It could have the right temperature but no magnetic field to shield it from radiation. It could have oceans but no land, or land but no water. From what we can tell, hitting the exact combination that allows life and keeps it going is trickier than it sounds. Earth, in that sense, is balanced on a narrow ridge between extremes. Too close to the sun and we'd overheat like Venus. Too far and we'd freeze like Mars. Too small and we wouldn't have held onto our atmosphere. Too big and our surface might be a crushing pressure cooker. Even the tilt of our axis, the size of our moon, and the presence of Jupiter, which helps shield us from excessive asteroid impacts, are part of the equation. The more we understand about planetary science, the more it feels like there's a long checklist for a world to survive long enough for intelligent life to appear, and yet the sheer number of stars and planets means that some fraction of them must check enough boxes. If Earth isn't alone in this category, then it's reasonable to imagine others have existed in the past. And if some of those others no longer exist as living worlds, the question becomes, what happened to them? Were they undone by forces beyond control, like the slow brightening of their star or a massive asteroid impact? Or were they undone from within, perhaps by their own life forms pushing the planet's systems past the point of recovery? Thinking about this can feel abstract until you bring it back to familiar territory. Imagine standing on a coastline here on Earth, looking out over the water. You know the tides will come and go, storms will rise and fall, and the land might slowly shift over centuries, but it all feels steady in the moment. Now imagine that same scene on a different planet, one that no longer has water. The rocks are the same, the shape of the coast is there, but the ocean is gone. The air is thin or toxic, and the sky holds a sun that feels wrong. The place might still be beautiful in a stark way, but it would carry the silence of something that used to be alive. That's what a failed world is. Not necessarily destroyed, but no longer able to support what it once did. In our own neighbourhood, Mars is the most obvious candidate for this kind of story. We see dry riverbeds, minerals that form in water, and polar ice caps. Billions of years ago, it may have had a thicker atmosphere and a warmer climate. But something changed. The planet's core cooled, its magnetic field faded, and the solar wind stripped away much of its air. The water either froze or escaped into space. Life, if it ever existed there, would have faced a shrinking window of possibility before conditions became too harsh. Today, Mars is a cold desert, and whatever history it had is locked away in rocks and dust. Venus offers another cautionary tale. It may have started with oceans, but its proximity to the sun and a runaway greenhouse effect turned it into a furnace. Its thick atmosphere is almost entirely carbon dioxide, trapping heat so effectively that the surface is hot enough to melt lead. Clouds of sulfuric acid swirl overhead. The crushing pressure is more than 90 times that of Earth's surface. Whatever chances Venus might have had for life were buried under an unstoppable chain reaction of heat and chemistry. Both of these planets remind us that being in the right place at the right time isn't enough. Conditions can change, sometimes slowly, sometimes abruptly. A planet that seems stable for hundreds of millions of years can cross a tipping point and never recover. That's part of why Earth's long stretch of habitability is so remarkable. It has survived asteroid impacts, ice ages, and shifts in climate that might have pushed other worlds over the edge. When you expand that thought to the galaxy, the picture becomes even more complex. Some stars are more volatile than others, sending out bursts of radiation that could strip a planet's atmosphere in moments. Some planets orbit in unstable systems, where gravitational interactions throw them off course over time. Others may form in regions with too much nearby activity, dense star clusters or areas near supernovas, where destructive events are more common. The environments that allow life to start are fragile, and the ones that allow it to continue are rarer still. If we think of the galaxy as a landscape, it's probably not a smooth field dotted with a few bright spots of life. It's more like a rugged terrain, full of valleys where conditions are too harsh, peaks where they're too brief, and occasional plateaus where life can take root and grow. Earth may be on one of those plateaus now, but it's worth remembering that plateaus don't last forever. Over the scale of millions or billions of years, climates shift, continents move, and stars evolve. Our own sun will eventually expand into a red giant, swallowing or scorching the inner planets. Long before that, Earth's habitability will change in ways we might not be able to control. All of this leads to the unsettling but logical possibility that many planets we would consider like Earth in their prime are no longer in that state. They might look fine from a distance, the right size, the right orbit, but up close, they've passed their moment. They're the cosmic equivalent of a house with the lights still on but no one inside. And if the galaxy is old enough for this to have happened many times, then it's possible we're living in a universe full of such worlds, silent reminders that habitability is temporary. This idea doesn't have to make us feel hopeless. In fact, it can give us a different kind of appreciation for what we have now. The fact that Earth is still in its window means we're experiencing something that might not be common at any given time. It also means we have the chance, and the responsibility, to avoid becoming just another name on that long, invisible list. Other planets may not have had that opportunity, or may not have recognized it in time. We do. And this is where our journey into the lives and deaths of worlds really begins, because before we can understand the fate of Earth, we have to understand what can cause a planet to fail. That means looking closer at our neighbours, and then farther out into the galaxy to see the patterns in those failures. If you could step outside the Milky Way and look down on it from above, you'd see a vast spiral of light, hundreds of billions of stars scattered across lanes of dust and gas. It would be easy to imagine that, in such abundance, life should be everywhere. But between those bright points of hope, there would also be darkness. In that darkness, hidden from view, are places that were once alive in ways we can barely picture, and are now nothing more than relics. You could think of them as entries in a cosmic cemetery, a collection of gravestones that no one has ever read, spread out over unimaginable distances. This is the graveyard of planets. It's not an official term in astronomy, of course. Scientists tend to use phrases like uninhabitable or sterile, but those words lack the weight of finality. Graveyard has a different tone. It reminds us that something was lost, that there was a before and an after, and whether we realise it or not, many of the worlds we study today may belong to this category. The only reason we don't recognise them as such is that we have no memory of what they were before. We arrive late to the story, seeing only the last pages. Some of these dead worlds never had much of a chance. They formed too close to their stars and were baked from the start, or too far and froze solid before anything interesting could happen. Others orbited stars that lived fast and died young, burning through their fuel and swelling into giants that consumed or scorched their planets. But the most haunting members of the graveyard are the ones that seem like they could have made it. They had the right size, the right temperature, maybe even oceans and atmospheres that could have supported life for millions of years. And yet, they didn't last. Venus and Mars, the cautionary tales in our own solar system, are the graves we can visit most easily. Their lessons are sobering. Stability is fragile, and the forces that maintain it can shift in ways that are irreversible. On Venus, the greenhouse effect that keeps Earth warm spiraled out of control. Carbon dioxide built up, trapping more heat, which released more CO2 from the surface, trapping even more heat. Once the cycle began, there was no stopping it. On Mars, the opposite happened. Its protective magnetic field collapsed, the atmosphere thinned, and the warmth bled away into space. In each case, the planet crossed a threshold and never came back. Those are just the examples we can see up close. The reality is that every star likely has its own history of successes and failures. With the thousands of exoplanets we've found, the patterns are beginning to emerge. Many orbit so close to their stars that they're tidally locked, with one side in perpetual daylight and the other in endless night. The day side is scorched, the night side frozen. In between, there may be a narrow twilight band where temperatures are tolerable, but it's not enough to sustain a stable planet-wide biosphere. Others are gas giants with no solid surface, or rocky worlds without atmospheres, stripped bare by stellar winds. And then there are the worlds we call super-Earths, planets larger than ours, some in the habitable zone. They sound promising, but many are likely covered in deep oceans with no exposed land, or wrapped in atmospheres so dense that their surfaces are unrecognisable as anything we'd call Earth-like. A few may have been habitable once, only to lose that balance when their stars changed, or their own geologies betrayed them. One of the more sobering ideas in planetary science is that even if a planet has life, there's no guarantee it will be there when you check back in 1 billion years. Conditions shift over time, stars slowly brighten as they age, changing the amount of energy their planets receive. Continents move, altering ocean currents and climate. Even the chemistry of the atmosphere can drift. On Earth, the presence of life itself has altered the environment dramatically, oxygenating the air, cooling the climate, reshaping the land. That's worked in our favour so far, but there's no rule that says it always will. On another world, the changes brought by life might set off a chain reaction that ends up making the planet less, not more, hospitable. The graveyard doesn't just hold planets that failed quietly. Some may have ended in sudden catastrophe. A large enough asteroid impact can reset a planet's ecosystem in a matter of days. A nearby supernova can bathe a planet in radiation, stripping its atmosphere and damaging its biosphere. A shift in the orbit of a massive neighbour could destabilise the planet's path, sending it into extreme seasons or even ejecting it from its star system entirely. Imagine a world with oceans and forests drifting into interstellar space, its surface freezing solid as it leaves its star behind. Life would end not with a slow decline, but with an abrupt plunge into permanent night. Some of these outcomes sound extreme, but they're not rare on cosmic timescales. Planets form in dynamic environments. They share their systems with other bodies that tug on them gravitationally. They exist in galaxies where stars are born, live and die in cycles of violence. We happen to live in a relatively quiet neighbourhood right now, but the universe is not by nature a calm place. This raises another point. The graveyard might not be permanent for every world in it. Some planets could, in theory, be revived. A frozen planet drifting in space might pass close to another star and warm up again. A planet that lost its atmosphere could regain one through volcanic activity or impacts from comets. Whether life could return is another question entirely, but habitability might be something that ebbs and flows over a planet's lifetime. If that's true, then the graveyard is more complicated than it seems. Some of its residents might not be gone forever, just lying dormant, waiting for the right conditions to return. Still, for most, the end is final. A runaway greenhouse effect won't reverse itself. A planet that's been swallowed by its star won't reappear. A collision that shatters a world leaves only debris. And even if a planet survives physically, the end of its biosphere marks the loss of everything that made it alive. When we talk about dead planets, we're really talking about the end of possibility. They may still be beautiful to look at, but they no longer hold the potential for something to grow, change, and thrive. What makes the concept of the planetary graveyard so powerful is that it forces us to think of worlds not as static objects, but as participants in a story with a beginning, middle, and end. Earth is somewhere in the middle of its story now. We're in the part where the conditions are still right, where life still fills the oceans and covers the land. But the middle isn't the end, and if we've learned anything from the planets around us, it's that endings come in many forms. The challenge for us is that we don't get to see the whole arc for most of these worlds. We arrive late and try to reconstruct what happened from the clues left behind. That's true for Mars and Venus, and it will be true for most of the exoplanets we study. Even with the most advanced telescopes, we're still reading gravestones without knowing the full inscriptions. There's a certain humility in that. It reminds us that our perspective is limited, and that the universe doesn't arrange itself for our convenience. We might want clear answers, neat timelines, and definite causes, but the graveyard doesn't give those easily. Instead, it offers patterns and possibilities, hints at the fragility of habitability, and the knowledge that we are not immune to the same forces. And so, when we think of the graveyard of planets, It's not just an exercise in cosmic archaeology, it's a warning and a mirror. It shows us what can happen and invites us to imagine our place among these countless worlds. Are we a permanent outlier, destined to survive where others fell? Or are we just one more planet in the long procession, walking toward a future we'd rather not see? The only way to start answering that is to look closer at the individual stories of these lost worlds, to see what they tell us about the path we're on. Some of those stories are right next door, waiting for us to piece them together. When we picture ghost worlds, our minds often jump to far-off exoplanets orbiting distant stars, the kind we can only detect as tiny dips in a star's light or subtle wobbles in its motion. But the truth is, we don't need to look across the galaxy to find them. Some of the most intriguing examples are right here in our own backyard, orbiting the same sun as we do, sharing our cosmic address. They're close enough that we've sent spacecraft to visit them, photographed their surfaces in high detail and even landed on them. And the more we've learned, the more they've begun to feel like ruins in the neighbourhood, places that might once have been alive in some sense, and now drift through time as empty shells. Mars, Venus, and several of the solar system's moons fit this description. Each has its own story, a different path to becoming what it is today. Taken together, they give us a valuable set of case studies in how a world can go from promising to desolate. And because they're so close, they're the ones we know best. Though even here there's more mystery than certainty. Mars is perhaps the most famous ghost world, partly because of how much it resembles Earth in certain ways. It's smaller, colder, and much drier now, but it has valleys, mountains, ice caps, and what appear to be ancient river channels carved into its surface. These features suggest a past very different from the planet we see today, one where liquid water may have flowed freely and pooled in lakes or seas. In fact, data from orbiters and rovers has revealed minerals that can only form in the presence of water, pointing to a time when Mars had a thicker atmosphere and a climate warm enough to support it. The leading theory is that Mars lost most of its atmosphere when its magnetic field weakened. Without that magnetic shield, the solar wind, a constant stream of charged particles from the sun, stripped away the air over millions of years. As the atmosphere thinned, surface pressure dropped, and water either froze or evaporated into space. Whatever life might have started there, if any, faced an increasingly hostile environment until survival became impossible. Today Mars still holds water, but it's locked up in ice caps and possibly in salty underground reservoirs. The surface is dry and barren, bombarded by radiation that makes it difficult for anything to live there now. Yet the signs of its wetter past are written across its landscape like faded inscriptions on a weathered monument. Venus tells a different kind of ghost story, one of too much heat rather than too little. Similar in size and composition to Earth, Venus may have started out with a temperate climate and oceans, but its proximity to the Sun meant it received more energy, and over time this triggered a runaway greenhouse effect. Water in the atmosphere evaporated into space, carbon dioxide built up, and temperatures soared. The surface today is hot enough to melt lead, with crushing air pressure and clouds of sulfuric acid. Any possibility of life as we know it was erased long ago. What makes Venus particularly unsettling is that it may have been Earth-like for hundreds of millions of years before this transformation happened. That means a planet can look fine for a long time and still fall into a death spiral it can't escape. If Mars and Venus are reminders that Earth's climate balance is fragile, the solar system's icy moons show us that habitability can take forms we might not expect. Europa, a moon of Jupiter, has an icy crust that hides a global ocean beneath. Enceladus, a moon of Saturn, sprays water vapour from cracks in its surface, hinting at liquid reservoirs below. Titan, another of Saturn's moons, has lakes and rivers, not of water but of methane and ethane, in a thick atmosphere that could shield potential life from radiation. These moons aren't dead in the same sense as Mars or Venus. Some might even be alive in ways we don't yet understand. But they are still ghost worlds in the sense that, from the surface, they're hostile and empty. If anything thrives there, it's hidden deep below, in conditions far from the sunlit environments we associate with life. They remind us that a world's surface appearance can be misleading, and that the line between failed and still holding on can be invisible to us. Studying these nearby examples is more than just an exercise in planetary tourism. There are test cases for understanding the many paths a world can take. If we can figure out why Mars dried up, why Venus overheated, and whether any of the icy moons harbour life, we'll have a much better sense of how common or rare Earth's stability really is. We'll also be able to refine our search for habitable worlds elsewhere, knowing what warning signs to look for. It's also impossible to study these worlds without a certain sense of reflection. Mars, with its ancient riverbeds, is a vision of what Earth might become if our atmosphere were stripped away. Venus is a warning of what could happen if greenhouse gases run unchecked. The icy moons hint at the possibility that life can persist in unexpected refuges, even when the surface seems utterly inhospitable. Together they form a kind of cautionary map for our own future, not predictions, but possibilities. The haunting thing is that even within this small set of neighbours, we see such a variety of outcomes, and that's in a single solar system, around a single star. Multiply that by the hundreds of billions of stars in the galaxy, and you start to realise how many ghost worlds there could be. Some would be obvious, their surfaces scarred by impacts or baked by heat. Others might look deceptively calm, hiding the fact that their days of supporting life ended eons ago. And if this is the case just in our corner of space, then Earth's place in the story isn't guaranteed to be permanent. We're here now, in the middle of our planet's habitable window, but there's nothing that says that window will stay open indefinitely. The ghost worlds next door show us how quickly, in geological terms, a planet can cross from livable to lifeless. They also show us that once that line is crossed, it's rarely crossed back. These nearby planets and moons are more than just points of interest for probes and telescopes. They're reminders that the conditions we take for granted are not universal, and that the boundary between a thriving world and a failed one can be thinner than we'd like to believe. The question isn't just how many worlds out there are alive, but how many used to be, and what that means for us. And that question becomes even more urgent when we remember that the solar system itself is just one grain of sand in the vast beach of the galaxy. Beyond our sun's reach are countless other stars, each with its own set of worlds. If we've already found ghosts among our closest neighbours, how many more might be waiting out there? Their stories untold. The only way to find out is to look deeper and further into places we've never been, searching for the same signs of past life we've learned to read here. Mars has been part of our imagination for as long as we've been able to see it in the night sky. Even without telescopes, ancient observers noticed its reddish colour and unusual movement among the stars, and they gave it the names of gods of war and strength. In modern times, as our understanding of the planets grew, Mars became the prime candidate for another Earth, a place that might have life, or at least might have had it once. Over the years, we've swung between thinking it's a living neighbour and a barren desert, but the more we've studied it, the more it seems like the truth lies somewhere in between. Mars today is lifeless on the surface, but there's strong evidence that it might once have been far more welcoming. The first real clue came not from spacecraft, but from telescopes. In the late 19th and early 20th centuries, astronomers like Giovanni Schiaparelli and Percival Lowell claimed to see linear features on the surface, which they described as canals. The word sparked public excitement, conjuring images of intelligent Martians building vast waterways to transport water across a dying planet. We now know these canals were optical illusions, but the idea stuck in the public imagination. The truth, revealed decades later by robotic probes, turned out to be both less dramatic and more fascinating. Mars does have channels and valleys that stretch for hundreds or even thousands of kilometres, but they were carved by rivers, not alien engineers. When NASA's Mariner missions in the 1960s and 70s sent back the first close-up images, the surface looked dry and cratered, like the moon. It was a disappointment to those hoping for signs of lush landscapes or alien cities. but scientists soon realised that this dry planet still held secrets. Viking orbiters and landers in the late 1970s showed branching valleys, flood plains, and sediment deposits that all pointed to liquid water in the past. Over time, with the help of newer missions like Mars Global Surveyor, Mars Odyssey, and the fleet of rovers that followed, the picture became clearer. Billions of years ago, Mars likely had a thicker atmosphere, warmer temperatures, and large bodies of water on its surface. One of the most compelling pieces of evidence is the presence of clay minerals and hydrated salts in the Martian soil. These minerals form in the presence of water, and their existence suggests that Mars once had lakes, rivers, and possibly even seas. The Gale crater, explored by the Curiosity rover, contains layered sediments that look strikingly like those formed by ancient lake beds on Earth. In some areas, these layers stretch for kilometres, recording a history of wet and dry periods over millions of years. If life ever took hold there, these lakes would have been prime habitats. So what happened? The leading theory centres on Mars' size and its internal heat. Smaller planets cool faster than larger ones, and as Mars' interior cooled, its core stopped generating the magnetic field that once shielded its atmosphere from the solar wind. Without that shield, the atmosphere was gradually stripped away. As the air thinned, surface pressure dropped, and liquid water could no longer remain stable for long. It either froze underground or evaporated into space. Over millions of years, the climate shifted from warm and wet to cold and dry, and any surface life would have been pushed to extinction, or driven underground if it could survive at all. It's possible that microbial life still exists beneath Mars's surface, protected from radiation and extreme cold. Recent detections of methane in the atmosphere, which on Earth is often produced by living organisms, have fueled speculation. Methane can also be generated by geological processes, so its presence isn't proof of life, but its seasonal fluctuation suggests something active is happening underground. Subsurface water, detected in the form of ice, and possibly briny liquid lakes, could provide the conditions for survival. For now, though, we don't have direct evidence either way. The fact that Mars may have been habitable billions of years ago makes it one of the most important targets in the search for life beyond Earth. If we could find fossils of ancient microbes or chemical signatures of biological activity in its rocks, it would be a discovery with enormous implications. It would tell us that life can arise on multiple planets in the same solar system, making it far more likely that it exists elsewhere in the galaxy. But it would also remind us that habitability can be temporary, and that even a planet that starts off promising can lose its grip on life. What's striking about Mars is how similar it might have been to Earth in its early history. Both planets formed from the same cloud of dust and gas around the Sun. Both had volcanoes, liquid water, and atmospheres. For a time, they may have been twin worlds, each with the potential to develop life. But their paths diverged sharply. Earth's magnetic field stayed strong, its atmosphere remained thick, and its climate stayed within a range where water could remain liquid on the surface. Mars, by contrast, became a frozen desert. We can speculate about how long Mars's habitable period lasted. It might have been only a few 100 million years, or it could have stretched for over 1 billion. Either way, in cosmic terms, that's not a long time. If life needs billions of years to evolve into complex intelligent forms, Mars might never have had the chance. That raises an interesting possibility. Perhaps the universe is full of planets where life begins, but never has time to develop beyond the simplest forms. These worlds might be covered in microbial mats, or host ecosystems just starting to take shape, when some shift in climate or geology wipes them out. From a distance, Mars still looks inviting. Its surface is not scorched like Venus or completely frozen like some of the outer moons. Its sky is a dusty orange, its mountains are taller than anything on Earth, and its canyons are deeper. If you were standing on the surface in a spacesuit, you might almost forget how hostile it really is. The air, though, is so thin you couldn't breathe it. The temperature at night drops low enough to freeze carbon dioxide. Dust storms can envelop the entire planet for weeks, blocking out the sun. It's beautiful, but it's also a reminder that beauty doesn't guarantee survival. What we see on Mars today is the end state of a planet's decline. Its rivers are gone, its seas have dried, and its once protective atmosphere has thinned to a wisp. And yet, in its rocks and soil, the memory of its earlier self is still there. Every rover wheel print, every scoop of regolith turned over by a robotic arm, is a small excavation of a world that almost made it. Mars forces us to think about how close a planet can come to being Earth-like and still end up lifeless. It also forces us to confront the fact that planets change. What's true today isn't guaranteed tomorrow, at least not in the long run. Earth's climate, oceans and atmosphere have all shifted over billions of years, and they will continue to do so. The difference so far is that our planet has managed to stay within the narrow range that allows complex life to survive. Mars didn't, and the reasons why are still being pieced together. If we do eventually send humans to Mars, they'll be walking on the surface of a place that once had flowing rivers and blue skies. A place where life may have existed long before life on Earth even began to take shape. And they'll be looking up at a sun that shines a little dimmer there, feeling the thinness of the air, knowing that they're standing in a vast silent reminder of how fragile a habitable planet really is. This is why Mars is more than just a scientific target. It's a story in progress, a case study in planetary evolution, and a warning. It shows us that being habitable once doesn't mean being habitable forever. And as we keep exploring, we'll learn more about how and why its story changed, and how that knowledge might help us keep Earth's story from ending the same way. And that leads naturally to the next neighbour in our solar system's gallery of ghost worlds, one that went the opposite direction from Mars, not freezing into silence but heating itself into a furnace. If Mars is a lesson in what happens when a planet loses too much warmth and air, Venus is the opposite extreme, a place that kept both, but in the wrong balance, and paid the price. It's close enough in size, mass and composition to Earth that we often call them planetary twins. In the early days of planetary science, it wasn't unreasonable to imagine that Venus might have been Earth's sister in habitability as well, a place with oceans, clouds and a stable climate. Instead, it has become one of the most hostile environments in the solar system. A world where the surface is hot enough to melt lead. The pressure is equivalent to being nearly a kilometre underwater, and the air is thick with carbon dioxide and clouds of sulfuric acid. What makes Venus so compelling isn't just its hostility, it's the likelihood that it didn't start out this way. Many planetary scientists believe that billions of years ago, Venus may have been temperate, with liquid water covering parts of its surface. The similarities between Earth and Venus suggest that both began with comparable amounts of water and similar atmospheric compositions. The difference lies in what happened next. The crucial factor is Venus's position. It's about 30% closer to the Sun than Earth, which means it receives roughly twice the amount of solar energy. On Earth, the balance between incoming sunlight and outgoing heat keeps the planet's surface within a range where water can remain liquid. On Venus, the extra energy may have tipped that balance. As the planet warmed, more water evaporated into the atmosphere, and because water vapour is a greenhouse gas, it trapped even more heat. This set off a positive feedback loop. Higher temperatures led to more evaporation, which led to more heat trapping, which led to still higher temperatures. Over time, this runaway greenhouse effect transformed Venus. The oceans boiled away. Water vapour in the upper atmosphere was broken apart by solar radiation, and the lighter hydrogen atoms escaped into space. With no water left to absorb carbon dioxide or weather rocks, CO2 built up in the atmosphere. Today, it makes up about 96% of the air on Venus, creating an incredibly thick blanket that traps heat with brutal efficiency. The result is a surface temperature of around 465 degrees Celsius, hotter than Mercury, even though Mercury is closer to the Sun. The clouds that swirl above Venus are another layer of its hostility. Made mostly of sulfuric acid droplets, they reflect much of the sunlight that hits the planet, making it bright in the night sky, but hiding its surface from view. Early radar studies and later spacecraft missions revealed a rocky volcanic landscape beneath those clouds, with vast plains, mountains, and thousands of volcanoes. Some of those volcanoes may still be active today, releasing gases that contribute to the dense atmosphere. One of the most unsettling aspects of Venus is how deceptive it is from a distance. To the naked eye, it's the brightest object in the night sky after the moon. It shines steadily, without the twinkle of stars, and it has been a point of wonder for cultures all over the world. The ancient Greeks and Romans associated it with their goddesses of love and beauty. The Maya tracked its movements with incredible precision. But the planet's beauty is entirely superficial. Beneath that shining exterior lies a place that could destroy a spacecraft in hours and a human in seconds. Our attempts to visit Venus have been brief and brutal. The Soviet Venera program in the 1970s and 80s managed to land several probes on its surface, but none survived for more than about 2 hours before succumbing to the heat and pressure. The images they sent back showed a barren, rocky plain under a yellow sky. No oceans, no signs of life, just a hostile wasteland. Later missions, like NASA's Magellan orbiter in the 1990s, mapped the surface in detail using radar, revealing features that hinted at a complex geological history. But despite decades of study, we still don't know exactly when Venus made its transition from potentially habitable to utterly inhospitable. There's even debate over whether Venus might have had habitable conditions for far longer than we once thought. Some climate models suggest that if Venus had slower rotation or a different atmospheric composition in its early days, it could have supported liquid water for hundreds of millions, perhaps even billions of years. If that's true, it means life had a real chance to arise there, and that possibility carries a heavy implication. A planet can be habitable for a long time and still lose that habitability. There's no permanent guarantee. For Earth, that's an uncomfortable lesson. While we are farther from the Sun and have a different atmospheric history, the mechanisms that drove Venus into its current state, runaway greenhouse warming, loss of water, changes in atmospheric chemistry, are not alien to us. They're physical processes that operate under the same laws of nature everywhere. The difference is one of degree, and that means the boundary between stability and collapse might be narrower than we like to think. Venus also complicates how we search for life on exoplanets. From a distance, a Venus-like planet can look a lot like an Earth-like planet. It's about the same size, has a thick atmosphere, and orbits in what might appear to be the habitable zone. Without detailed data about its atmosphere and surface conditions, we could mistake it for a potential home for life. That's why understanding Venus is so important. It teaches us what a failed Earth can look like, and it gives us the tools to avoid false optimism when studying distant worlds. There's another reason Venus fascinates scientists. The question of whether life might exist there still, not on the surface but in the clouds. At an altitude of about 50 kilometers, the temperature and pressure are much more Earth-like, and there are traces of water vapor. In 2020, researchers reported detecting phosphine gas in Venus's atmosphere, a chemical that, on Earth, is associated with biological activity. The finding was controversial and has been questioned by other scientists, but it reignited interest in the idea that microbial life could survive in the acidic clouds. Even if this turns out to be a false alarm, it underscores how little we truly know about our neighbour and how easily it can surprise us. Venus forces us to rethink what it means for a planet to be like Earth. The similarities in size and composition make the differences in outcome all the more dramatic. It's a reminder that planetary evolution isn't just about where a world starts. It's about how it changes over time and how sensitive that process can be to initial conditions. A few million kilometers closer to the Sun, a slightly different atmosphere, a shift in volcanic activity. Any of these could alter the trajectory of a planet's climate in ways that are irreversible. In the broader story of failed worlds, Venus stands as the example of a world that had the resources to thrive but turned them into a trap. Its dense atmosphere keeps it hot, its heat fuels volcanic activity, and that activity releases more gases that maintain the thick atmosphere. It's a self-sustaining cycle, but one that sustains only its own hostility. If Mars is a frozen tomb, Venus is a burning prison. And yet, despite its extremes, Venus remains a vital part of our understanding of planetary habitability. It shows us that the line between success and failure is thin, and that even small differences in a planet's position or makeup can have massive consequences over geological timescales. It also reminds us that planets are not static. They evolve, sometimes in ways that make them more habitable, and sometimes in ways that seal their fate. As we study Venus and Mars side by side, we see two very different failures, each with its own causes, but both leading to the same outcome. A world where surface life, if it ever existed, is no longer possible. And when we step back and look beyond these two, we see that they are not exceptions. Across the solar system, and likely across the galaxy, there are countless other worlds that followed similar paths. Some froze, some burned, some might have lingered in a marginal state before tipping one way or the other. Our next stop in this exploration of failed worlds takes us to some of the most intriguing places in the solar system, places that may never have reached full habitability on the surface, but that could hold life in hidden, protected environments. When we think about places where life might exist, our minds usually go straight to planets. It's an understandable habit. After all, Earth is a planet, and it's the only example of a living world we know for certain. But if we take a closer look at our own solar system, it turns out that some of the most intriguing candidates for habitability aren't planets at all. They're moons. And not just moons that quietly orbit gas giants like ornaments in the night sky, but worlds in their own right, with oceans, ice, atmosphere, and in some cases chemistry, that hints at the possibility of biology. The story of these moons is different from Mars or Venus. They've never been fully Earth-like on the surface. They haven't had sprawling continents, breathable air, or open seas reflecting sunlight. Instead, they live under constant extremes, either buried in ice, smothered by thick haze, or locked in deep cold far from the sun. On the surface, they appear lifeless. But beneath that surface, in hidden environments shielded from radiation and extreme temperature swings, there may be, or may have been, the conditions for life. These are the almost worlds. They didn't quite make it as surface habitats, but they still hold the potential for something remarkable. Europa, one of Jupiter's largest moons, is a prime example. At first glance, it's an icy wasteland, a smooth, bright surface crisscrossed with dark lines and scars where the ice has cracked and shifted. There are few impact craters, which suggests the surface is young and constantly reshaped. What makes Europa special is what lies beneath, a global ocean of liquid water, kept from freezing solid by heat generated from tidal flexing. As Europa orbits Jupiter, the giant planet's gravity pulls and stretches it, creating friction inside its interior. That friction generates heat, which keeps the water beneath the ice in a liquid state. By most estimates, Europa's ocean could be twice the volume of all Earth's oceans combined. Liquid water is one of the key ingredients for life as we know it, and Europa has it in abundance. It also has the potential for chemical energy, supplied by interactions between the ocean and the rocky sea floor. On Earth, similar environments at the bottom of our oceans, hydrothermal vents, are home to rich ecosystems of organisms that thrive without sunlight, feeding on chemical reactions instead of photosynthesis. If Europa has anything like that, it could be one of the most promising places for life beyond Earth. Enceladus, a small moon of Saturn, offers a different but equally fascinating case. For years, it was thought to be just another icy body, until the Cassini spacecraft revealed something unexpected. Plumes of water vapour and ice particles erupting from cracks near its south pole. These geysers shoot material hundreds of kilometers into space. An analysis of the particles shows that they contain organic molecules, salts and other chemicals associated with water rock interactions. Like Europa, Enceladus is believed to have a subsurface ocean warmed by tidal heating. The fact that it actively vents its ocean into space makes it one of the easiest places in the solar system to sample for signs of life. We wouldn't have to drill through kilometers of ice, just fly a spacecraft through the plumes. Then there's Titan, Saturn's largest moon, and the only moon in the solar system with a thick atmosphere. Its surface is cold, around -179 degrees Celsius. But it has lakes and rivers of liquid methane and ethane, as well as rain and clouds made of hydrocarbons. Titan's atmosphere is rich in nitrogen and contains complex organic molecules. It's not warm enough for liquid water to exist on the surface, but models suggest there may be an internal ocean of water mixed with ammonia beneath the icy crust. Titan is unique because it's not just a potential home for water-based life. It also offers the possibility of life with an entirely different chemistry, using methane instead of water as a solvent. If such life exists, it would expand our definition of what's possible in biology. Other moons, like Ganymede and Callisto around Jupiter, or Triton around Neptune, may also have subsurface oceans. While we know less about them, they add to the growing list of places where habitability might hide in plain sight, not in lush sunlit environments, but in the dark, under layers of ice. These moons remind us that surface conditions aren't the whole story, and that a world can be harsh on top while harbouring something very different below. What sets these moons apart from the failed planets we've already discussed is that their habitability has always been indirect. They never had thick, warm atmospheres or wide-open seas under the sun. They aren't failed versions of Earth. They're worlds that took a different path from the start. Their almost status comes from the fact that, while they might never have been truly habitable in the way we imagine, they could still support life in protected environments. And if life exists there, it would mean that even worlds far from the sun, orbiting gas giants instead of stars, can join the ranks of the living. The challenge, of course, is getting proof. Europa's ocean is hidden under tens of kilometers of ice. Enceladus's plumes are tantalizing but rare, and require carefully timed flybys to study in detail. Titan's surface is shrouded in haze, and its subsurface ocean is even more difficult to detect. Yet the technology to explore these worlds is advancing. NASA's Europa Clipper mission, set to launch in the coming years, will conduct multiple close passes of Europa, mapping its surface and searching for signs of recent activity that might connect the ocean to the surface. Other proposed missions aim to return to Enceladus, to sample its plumes more directly, or to send landers to Titan to study its chemistry up close. These efforts are not just about finding life, they're also about understanding how common the ingredients for life are and how many different kinds of environments can support it. If even one of these moons turns out to have life, whether it's microbial, chemical, or something we've never seen before, it would show that life is not confined to Earth-like planets in the habitable zone. That would make the galaxy feel much more alive, and it would also expand our thinking about the graveyard of worlds. A planet or moon that looks dead on the outside might still be alive in ways we can't see. At the same time, the almost nature of these moons is a reminder that life can be pushed into the margins. If Europa's ice were thicker, or its tidal heating weaker, its ocean might have frozen solid long ago. If Enceladus didn't vent into space, we might never suspect its ocean exists. If Titan didn't have such an unusual atmosphere, it might be just another icy rock. These worlds are fragile in their own way, and whatever habitability they have could be lost if their delicate balance shifts. In the context of the larger question, whether Earth is one of many failed worlds, these moons are an important piece of the puzzle. They show that habitability is not an all-or-nothing state. Worlds can exist in a grey area between alive and dead, where the surface tells one story and the interior tells another. They also suggest that when we search for life, we should look beyond the obvious, because life might not just survive in unexpected places, it might thrive there. And perhaps most importantly, they hint at a sobering truth. If life can arise in these hidden oceans, it could also die there, silently, without leaving any obvious mark on the surface. A moon might go from almost to never, without anyone to witness it. In that sense, the moons that almost made it are not just places of possibility, they're also reminders of how easily possibility can fade. From here, our search for failed worlds will take us beyond our own solar system, into the realm of probability and scale. The idea that Earth might be just one of many attempts the universe has made at producing a world like ours. And in that vast set of attempts, most will not last. When we look at our own solar system, we see a mix of outcomes. Earth, which supports life in extraordinary variety and complexity. Mars, which may have once been warm and wet but is now frozen and dry. Venus, which may have once had oceans but now is a furnace of carbon dioxide and acid clouds. The icy moons, some hiding oceans that might be full of potential, others silent and frozen. All of them orbiting the same star, all formed from the same disk of dust and gas, yet ending up in such different states. This variation is a reminder of something that's easy to overlook, that the conditions which make a planet habitable are not just rare. They are the result of chance layered on top of chance. The cosmic lottery is a way to think about this. Imagine the formation of a solar system as a process of countless random draws. The initial composition of the gas and dust cloud, the exact distances of the planets from their star, the timing and scale of asteroid impacts, the tilt of a planet's axis, the presence or absence of a magnetic field, the balance of greenhouse gases, the size of nearby moons, the stability of neighbouring planets. Each one of these factors influences whether a world ends up with conditions that allow life to emerge and persist. Change any one of them by enough, and the outcome changes with it. Earth hit the jackpot in ways we're still learning to appreciate. Our distance from the sun keeps us in a temperature range where liquid water can exist on the surface. Our atmosphere is thick enough to retain that water, but not so thick that it traps too much heat. Our magnetic field shields us from solar and cosmic radiation. Our large moon stabilizes our tilt, preventing extreme swings in climate. Our plate tectonics recycle carbon dioxide and keep our climate in check over geological timescales. Even the chaos of asteroid impacts played a role, delivering water and organic molecules while not being frequent enough to sterilize the planet completely. But none of this was guaranteed. Move Earth a little closer to the sun, and we might have suffered Venus's fate. Move it farther away, and we might have frozen like Mars. Remove the moon, and we might have experienced chaotic climate swings that made complex life impossible. Lose the magnetic field, and the solar wind might have stripped away our atmosphere. Without plate tectonics, carbon dioxide might have built up or vanished into the crust, pushing us into a permanent hothouse or ice age. Now imagine scaling this idea up to the galaxy. There are hundreds of billions of stars, each with its own system of planets. Many of those planets may start with some of the ingredients for life, but the odds of them landing in the exact right combination, not just once, but remaining there for billions of years, are slim. Even if life emerges on some of them, the same hazards that threaten Earth's stability could push them into the category of failed worlds. In other words, winning the lottery isn't enough. You have to keep winning it over and over for as long as life needs to survive. This perspective changes the way we think about habitability. It's not just about the habitable zone around a star, where temperatures are right for liquid water. That's just the first draw in the cosmic lottery. The rest of the draws happen over time, and they're about stability, about whether a planet can stay in that narrow zone of habitability for long enough to develop and sustain life. The evidence from our solar system suggests that many worlds start in promising positions but drift out of them. The reasons can be subtle, like changes in a star's brightness over billions of years, or dramatic, like massive impacts or volcanic upheavals. The cosmic lottery also helps explain why we might expect to find many more failed worlds than successful ones. For every Earth-like planet that manages to maintain stability for billions of years, there could be dozens that almost made it but lost their habitability too soon. Some might fail early, like Venus, spiralling into a runaway greenhouse effect before life can gain a foothold. Others might fail late, like Mars, losing their atmosphere after hundreds of millions of years of potential habitability. The result is a galaxy full of worlds that tell incomplete stories, beginnings without middles, middles without endings. There's another layer to this, the role of sheer luck. Even with all the right conditions, random events can change everything. On Earth, the asteroid impact that wiped out the dinosaurs could have been larger, or could have struck a different part of the planet, leading to a mass extinction that left no survivors. A nearby supernova could have bathed Earth in radiation, stripping the ozone layer and triggering ecological collapse. A slight change in the timing or location of volcanic activity could have pushed the climate past a tipping point. These are the equivalent of pulling a bad number in the lottery after a long run of good ones. This doesn't mean life is hopelessly fragile. After all, Earth has survived for billions of years. But it does mean that our survival is a combination of resilience and luck. The resilience comes from Earth's systems, which can buffer against some changes. The luck comes from avoiding disasters that could overwhelm those systems. In the cosmic lottery, you can improve your odds, but you can't control every draw. When we search for life beyond Earth, we're essentially searching for other jackpot winners. But it's worth remembering that even jackpot winners don't last forever. Stars age, planets change, and the conditions for life shift. The question isn't just whether life exists somewhere else now, it's whether it can persist. The graveyard of planets we've already imagined is full of examples of worlds that may have won the early draws but lost later ones. This way of thinking has a humbling implication. If we do find life elsewhere, it's probably temporary, just like ours. Even if a planet has been stable for billions of years, there's no guarantee it will remain so indefinitely. The cosmic lottery never stops. Every world is playing, whether it wants to or not, and eventually the odds catch up. That doesn't mean life is doomed everywhere, but it does mean that permanence is rare. It's tempting to think that intelligence, technology, or advanced civilization might be able to beat the odds, to protect a planet from the same fates that befell others. And maybe that's true to an extent. We might learn to manage our atmosphere, prevent runaway warming or cooling, deflect asteroids, or even move our civilization to new worlds if necessary. But those are responses to known threats. The cosmic lottery includes unknown ones as well, and history shows that nature often finds ways to surprise us. For now, Earth is holding its winning ticket. We're in the right place, with the right balance of conditions, at the right time. But the more we study the other worlds in our solar system and beyond, the more we realise how precarious that position is. We're not the inevitable outcome of planetary evolution. We are the result of a long chain of improbable events, any one of which could have gone differently. And so, as we move deeper into our search for life, we should keep the cosmic lottery in mind. It doesn't just shape the odds of finding other living worlds, it also shapes our understanding of our own, and the realization that one day even the luckiest planets can join the graveyard. From here, the path leads beyond probability into observation, into the work of actually finding those distant worlds and learning their stories so we can see how many have played and how many have lost. If the cosmic lottery is about chance, the great filter is about survival. It's the idea that somewhere along the path from lifeless rock to a thriving, advanced civilization, there are obstacles so difficult that almost nothing makes it past them. In other words, there may be steps in the evolution of life and society that are not just improbable, but nearly impossible. Bottlenecks that most worlds never squeeze through. And if that's true, it could explain why, in a galaxy full of planets, we have yet to see clear signs of anyone else. The Great Filter is a concept often discussed in the context of the Fermi Paradox. The question of why, given the age and size of the galaxy, intelligent life doesn't seem to be everywhere. There are hundreds of billions of stars, billions of planets in habitable zones, and countless opportunities for life to arise, yet the skies remain silent. One possible answer is that there's a point in the timeline of life where the odds of progressing to the next stage drop so low that almost no one makes it through. That point, whatever it is, would be the Great Filter. The steps leading from raw chemistry to a civilization capable of sending signals across space are many. First, you need a planet in the right position, with the right ingredients and stable conditions. Then, life has to arise, perhaps from a combination of organic molecules, energy sources and environmental catalysts. Once life exists, it has to become more complex, evolving from single-celled organisms to multicellular forms. Those multicellular organisms have to develop intelligence, then technology. And even after technology emerges, a civilization has to survive long enough to explore the stars. At any one of these steps, the process could stall or fail entirely. If the Great Filter lies early in the sequence, it means that life itself is rare. Perhaps the origin of life, a biogenesis, is so unlikely that it only happens once in a trillion tries. In that case, most habitable planets stay empty. They may have oceans, atmospheres, and stable climates, but they never cross the line into biology. If that's the case, Earth is special because it got past that first improbable barrier. If the Great Filter lies later, it paints a different picture. Life might arise fairly often, and even become complex, but then something happens that prevents it from lasting. Maybe mass extinctions, climate instability, or asteroid impacts wipe the slate clean before intelligence can evolve. Or maybe intelligence does evolve, but civilizations destroy themselves through war, environmental collapse, or technological accidents before they can spread beyond their home worlds. There's also the unsettling possibility that the Great Filter is ahead of us. In that case, the reason we don't see other civilizations is because they all eventually encounter the same deadly challenge, one we haven't faced yet. It could be something obvious, like the difficulty of managing advanced technology without self-destructing, or something subtle, like slow planetary changes that erode habitability beyond repair. If the Great Filter is in our future, then the silence of the galaxy isn't a sign that we're alone, it's a warning. The graveyard of worlds in our own solar system offers hints about where the Great Filter might operate. Mars shows that even a potentially habitable world can lose its atmosphere and water over time. Venus shows that a stable climate can tip into runaway heating. The icy moons show that habitability can exist, but remain locked away from easy access, perhaps forever. None of these worlds made it past the first few steps toward life as we know it. If the galaxy is full of similar examples, it suggests the early stages of habitability are fragile, and many worlds may never get past them. On Earth, life got its start quickly after the planet cooled, which suggests that the origin of life might not be the most difficult step. For nearly 3 billion years, however, that life remained microscopic. Multicellular organisms didn't appear until about 600 million years ago, and humans have only existed for a tiny fraction of that time. This raises the possibility that the transition from simple to complex life is the real bottleneck. If so, most living worlds might be stuck at the microbial stage, alive, but not capable of building civilizations. And then there's the survival question. Human civilization is less than 10,000 years old, a blink in geological terms. In that time, we've developed tools that can alter the planet's climate, split atoms, and send probes to the edges of the solar system. We've also come close to self-destruction more than once. The modern world runs on systems that are both powerful and fragile, and it's not hard to imagine how a series of poor choices or bad luck could end the experiment. If other civilizations face similar vulnerabilities, it would explain why none have lasted long enough to fill the galaxy. The Great Filter, then, might not be a single event or threshold. It could be a combination of challenges that, taken together, are almost impossible to overcome. A planet might survive asteroid impacts but fail to regulate its climate. A species might develop intelligence but never learn to cooperate at the scale needed to manage its resources. A civilization might master technology but lack the foresight to avoid catastrophic misuse. In each case, the result is the same. The world falls into the category of failed planets, joining the silent majority. If this sounds bleak, it's worth remembering that the Great Filter is still a hypothesis. We don't know where it is, how strong it is, or whether it's the same for every world. It's possible that Earth has already passed the hardest parts, that our existence as an intelligent technological species means we've beaten the odds. It's also possible that our future will depend on recognizing the dangers that others may not have survived. Either way, the concept forces us to take a broader view. It reminds us that life's path is not a smooth incline toward progress, but a precarious climb past cliffs and drop-offs. Every success story is the result of avoiding countless potential failures, and in the grand scale of the galaxy, success may be the exception, not the rule. When we think about Earth in this context, it becomes clear that our survival isn't just about maintaining habitability, it's about actively navigating the challenges that have ended otherworld stories. Whether the Great Filter is behind us or ahead, the graveyard of planets is a reminder that the universe doesn't owe us permanence. It gives us conditions, and we have to work to keep them. From here, the next step is to look at what we're doing now, both the risks we face and the ways we might try to push past them, to see whether we're building a path toward long-term survival or drifting toward the same fate as the countless silent worlds out there. If there's one lesson the other worlds in our solar system seem to keep offering, it's that habitability is not a permanent state. Even when the right conditions come together and life starts, there's no promise it will stay. Planets and moons are dynamic places. Their surfaces, atmospheres and interiors change over time, sometimes gradually, sometimes abruptly, and those changes can tip the balance in ways that life can't adapt to quickly enough. It's one thing for a planet to never become habitable in the first place, but it's another for it to cross that threshold, allow life to begin, and then lose it. Those cases are the ones that truly drive home how fragile the whole process is. We don't have a confirmed example of a once-living planet that's now entirely dead, but Mars may be the closest candidate. The evidence for its ancient rivers, lakes, and possibly seas suggests it could have been a cradle for microbial life billions of years ago. If life did take hold, it didn't hold on, at least not in any form we can easily find today. A changing climate, the loss of its magnetic field, and the stripping away of its atmosphere would have pushed surface life into a survival crisis. Maybe some organisms adapted to underground niches, maybe others froze into permanent dormancy, but the thriving surface ecosystems that might have existed would have been erased. That same story could have played out countless times across the galaxy. Imagine a world orbiting a quiet star in its habitable zone, covered in shallow seas and green coastlines, with an atmosphere rich enough to keep it warm and wet. Microbes emerge in the water, evolving into more complex forms over millions of years. Then something changes. The star becomes more active, sending bursts of radiation that strip the atmosphere. Or the planet's internal heat fades faster than expected, shutting down volcanic outgassing that replenishes its air. Or a massive impact tilts its axis, plunging it into an extreme climate cycle it can't escape. In any of these cases, the ecosystem collapses. The planet still orbits in the right place, but the surface is barren again. The fact that life appeared quickly on Earth after it became stable might suggest that starting life isn't as rare as we sometimes think. But if starting is relatively easy, and staying is hard, the universe could be full of worlds with fossils and empty landscapes, places where life had a beginning, but never a long-term story. From a distance, such planets might even look habitable for a while. Their atmospheres could hold traces of oxygen or methane left over from biology, but those traces would fade as the chemistry of the air returned to equilibrium without living processes to maintain it. The tricky part is that from our point of view, these worlds might be hard to distinguish from still living ones. If we find a planet with certain gases in its atmosphere, we might celebrate it as a likely home for life, only to discover later that those gases are relics of a vanished biosphere. It's the cosmic equivalent of finding an abandoned building with the lights still on. The electricity is running, but nobody's home. The factors that can cut a living planet's story short are varied. Changes in a planet's orbit can slowly shift its climate out of the habitable range. Geological processes can either overproduce or underproduce greenhouse gases, throwing temperatures out of balance. The death of a protective magnetic field can expose the surface to lethal radiation. Large impacts can sterilize vast regions, or even the whole planet if they're powerful enough. And sometimes the change is driven by the life itself. On Earth, for example, the rise of photosynthetic organisms billions of years ago flooded the atmosphere with oxygen, triggering the Great Oxidation Event. While oxygen is vital for many forms of life today, at the time it was a toxin to much of the existing biosphere, causing one of the earliest known mass extinctions. When we think about intelligent life, the list gets longer. A civilization might develop technologies that alter the planet's atmosphere or climate faster than natural systems can adjust. Overuse of resources, conflicts, or unintended side effects of innovation could all contribute to a collapse. In those cases, life isn't just reacting to changes in the environment, it's creating them. And while humans have only been capable of such changes for a short time, the impact has been significant enough to raise questions about how long our own favourable conditions will last. What makes the idea of a life that begins but doesn't last so haunting is the silence it leaves behind. A planet that loses its biosphere doesn't leave an obvious marker for passing civilizations to see. Its rocks and dust carry the story, but only in forms that require close inspection to read. Isotope ratios in ancient sediments, fossilized cells in mineral veins, chemical imprints in weathered layers. Unless someone visits in person or sends probes, the loss goes unnoticed. The galaxy could be filled with the ruins of ancient life, invisible to anyone who isn't looking closely enough. It's possible that our own world has skirted this fate more than once. Earth's history includes multiple mass extinction events, some of which wiped out the majority of species at the time. Each time, life rebounded, but there's no law that says it had to. A slightly larger asteroid, a more extreme volcanic episode, or a longer-lasting ice age might have ended the rebound entirely. If that had happened in the distant past, Earth could be one of those quiet worlds now, with only geological whispers to hint that it was ever alive. The lesson, if there is one, is that being alive is not the same as being safe. Life is adaptable, but it's not invincible. The conditions that support it can be temporary, even on planets that seem well suited to it. And while resilience can buy time, it can't stop the clock forever if the underlying systems are shifting out of balance. For scientists searching for life beyond Earth, this means being prepared for disappointment. We might find signs of life in the spectrum of a distant planet's atmosphere, only to discover that those signs belong to a biosphere that's already gone. We might land probes on a world that once teemed with microbes, only to find their remains preserved in ice or rock. Each of these would still be a groundbreaking discovery, proof that life exists elsewhere or has existed. But it would also remind us how rare it is to find a world that's still in the middle of its story. And for us, here and now, it's a reminder of our own position in that story. We are living through one of the rare stretches of time in which our planet has both the conditions for life and the life to make use of them. We don't know how long that will last, but we know that it won't last forever unless we make it last. That may mean learning to protect the systems that keep us stable, preparing for changes we can't prevent, and understanding that the universe's default state might not be life, but the absence of it. From here, the focus shifts to the forces that can erase life not just locally, but on a scale large enough to sweep across whole star systems. The cosmic events that turn potentially thriving worlds into members of the silent majority, regardless of how well they were doing before. If a planet is lucky, its biggest challenges are slow, giving life time to adapt. Shifts in climate, gradual changes in atmosphere, even the slow brightening of its star can be met with migration, evolution, or changes in behaviour. But not every threat moves at that pace. Some arrive suddenly, with enough force to undo millions of years of progress in moments. These are planetary extinction events, disasters so powerful they don't just change the course of life, they erase it outright, or cut it back to the barest fragments. On Earth, we've had close calls, and more than a few direct hits. The fossil record shows multiple mass extinctions, moments when a significant percentage of species vanished in geologically short spans of time. The causes vary: massive volcanic eruptions, asteroid and comet impacts, shifts in ocean chemistry, global glaciations, and even biological changes like the rise of oxygen in the atmosphere. Each one left the planet looking very different afterward, both in terms of who survived and how the ecosystems functioned. And yet, in every case so far, life has recovered. At least here. There's no guarantee other worlds have been so fortunate. The most famous example, and perhaps the most dramatic, is the asteroid impact that ended the reign of the dinosaurs 66 million years ago. The object, around 10 kilometers across, struck near what is now the Yucatan Peninsula, releasing more energy than billions of nuclear bombs. The immediate effects were catastrophic for anything nearby, but the global aftermath was even worse. The impact threw enormous amounts of dust and vapor into the atmosphere, blocking sunlight for months or years. Temperatures dropped, photosynthesis stalled, and food chains collapsed. Around 3/4 of all species went extinct. Events like that are not unique to Earth. Any planet with a thin enough atmosphere for large objects to reach the surface will face the same risk. The solar system is full of evidence. Craters on the Moon, Mars, Mercury, and even some of the icy moons show that impacts have been common throughout history. In the early days of a planetary system, they're even more frequent, as leftover debris from planet formation sweeps through orbits in unpredictable ways. For life trying to get started, this bombardment phase can delay or prevent any real stability. Volcanism can also be a killer on a planetary scale. On Earth, the Siberian Traps eruptions around 252 million years ago are linked to the Permian Triassic extinction, the deadliest known, wiping out about 90% of marine species and 70% of land species. These eruptions lasted hundreds of thousands of years, pumping massive amounts of carbon dioxide and methane into the atmosphere. The result was extreme global warming, ocean acidification, and a collapse of ecosystems worldwide, a planet with more active volcanism than Earth, or one without mechanisms to reabsorb greenhouse gases, could find itself in a runaway climate shift that ends habitability permanently. Star behaviour is another wild card. A nearby supernova, gamma-ray burst, or even an unusually strong solar flare could deliver lethal doses of radiation to a planet's surface. Such events can strip away parts of the atmosphere, damage the ozone layer, and trigger cascading ecological collapses. Unlike impacts or eruptions, there's nothing a planet can do to shield itself from cosmic radiation on that scale. For life on a world unlucky enough to be in the wrong place at the wrong time, these events are simply game over. Ice ages, while less dramatic in a single moment, can also drive extinction on a global scale if they're severe enough. Snowball Earth events, when the planet is almost entirely covered in ice, may have happened more than once in our own past. While some life can survive in isolated pockets, such conditions reduce available habitats drastically, and recovery depends on whether there are enough surviving niches to repopulate the planet once the climate shifts again. A planet without strong internal heat sources or without the right atmospheric mix might never escape a snowball state once it enters it. Biology itself can also trigger planetary-scale extinction events. The Great Oxidation Event around 2.4 billion years ago was caused by cyanobacteria producing oxygen through photosynthesis. At the time, oxygen was toxic to most life, and its rise in the atmosphere caused a massive die-off. While Earth eventually adapted, the same kind of transformative shift in atmospheric chemistry could happen elsewhere, and it might not always result in a stable, life-friendly environment afterward. The sobering truth is that extinction events don't have to completely sterilize a planet to qualify as failures in the context of long-term habitability. If they cut back life to only the simplest forms, or destroy complex ecosystems without recovery, the planet might never see advanced life again. Evolution takes time, and some planetary environments may never give it that time once they've been reset. One of the challenges in thinking about planetary extinction events is that they don't always leave obvious markers visible from afar. From light years away, a planet that lost most of its life in a volcanic apocalypse might still look much the same as one with thriving ecosystems. Its atmosphere could contain familiar gases, its oceans could still reflect sunlight in the same way, and its orbit would remain unchanged. The difference would only be clear on the surface, in the absence of forests, reefs, and the subtle chemical balance maintained by living systems. This means that when we search for life elsewhere, we might encounter worlds that appear promising but have already suffered one of these catastrophes. We could be looking at the aftermath without realizing it, mistaking a quiet planet for one that's still alive. It's another reason the galaxy might seem silent even if life has been common in the past. The survivors of planetary extinction events may not be detectable from where we sit, and the truly dead worlds are even harder to spot. For Earth, the history of mass extinctions is a reminder that our current stability isn't permanent. The risks that shaped our past still exist, and new ones can emerge. While we can't prevent every possible disaster, understanding them gives us a chance to prepare, whether that means monitoring near-Earth objects, studying volcanic patterns, or tracking the behaviour of our sun. These efforts don't just protect us now, they're part of the broader challenge of avoiding the fate of the countless worlds that never recovered from their worst days. And of course, planetary extinction events aren't always natural. The introduction of intelligent life capable of altering its environment on a massive scale adds a new category to the list, one where the cause of collapse is internal rather than external. That's where our exploration next turns, to the ways a planet can lose its habitability because of the very life it supported. When we think about extinction events, we often imagine forces beyond the control of life, asteroids, volcanic eruptions, or the unpredictable violence of the cosmos. But sometimes the end of a planet's stability isn't delivered from the outside, it comes from within. A civilization can be both the pinnacle of a planet's evolutionary story and the reason that story ends sooner than it might have. It doesn't take an asteroid to end an age. Sometimes it just takes the right combination of complexity, ambition, and miscalculation. On Earth, human civilization is young. In geological time, it's barely a blink. A few thousand years since the first cities, a few centuries since the Industrial Revolution, a few decades since our technology became capable of changing the atmosphere and climate on a planetary scale. This rapid growth has brought extraordinary achievements, from medicine and engineering to exploration and communication. But it has also introduced risks that no other species in our history has had to manage. We're capable not only of altering the conditions that sustain us, but of doing so faster than the planet's natural systems can respond. Civilizations collapse for many reasons, and history is full of examples. The Mayan cities of Central America, the once powerful societies of the Indus Valley, the Easter Island culture, the Roman Empire, all rose to heights of influence before declining or disappearing entirely. Each collapse had its own combination of causes: environmental changes, resource depletion, political instability, conflict, disease, or economic breakdown. In every case, the complexity of the civilization that made it successful also made it vulnerable. Systems that were once strengths became liabilities when circumstances shifted. The difference now is scale. Ancient collapses were local or regional. The failure of one society didn't bring down all human life. Today, our civilization is interconnected to the point where a breakdown in one part of the system can ripple across the whole planet. Food production, energy supply, transportation, communication, all are global networks. That makes them efficient and powerful, but it also means that failures in one part can cascade in ways that are difficult to contain. Environmental stress is one of the most common threads in the collapse of past civilizations, and it's a risk for us as well. Overuse of resources, deforestation, soil degradation, and water scarcity have all contributed to historical declines. In a global civilization, these pressures don't just affect one region, they can create widespread instability. Climate change adds another layer, altering weather patterns, shifting agricultural zones, and increasing the frequency of extreme events. The speed of these changes matters as much as their magnitude. Ecosystems and societies alike struggle to adapt when conditions shift too quickly. Conflict is another recurring factor. As resources become scarce or competition increases, tensions can escalate into wars that further strain the systems holding a civilization together. Technological advancement changes the scale of this threat as well. In the past, war could devastate cities and regions, but now it has the potential to disrupt or even end global stability. Weapons capable of destroying large parts of the biosphere, either directly or through their aftermath, mean that a single conflict could push the planet into a state from which recovery is unlikely. There's also the risk of technological accidents, disasters not born of intent but of complexity. The more advanced a society becomes, the more it relies on systems that few individuals fully understand. A failure in one of these systems, whether it's a power grid, a communications network, a data infrastructure, or a biosafety protocol, can have consequences far beyond its original scope. When those systems are tied to essential functions like food supply or healthcare, the effects can multiply quickly. Economic instability can act as both a cause and a symptom of collapse. A society that depends on constant growth can be shaken by downturns it isn't prepared for. Disruptions in trade, resource shortages, or loss of confidence in institutions can lead to a feedback loop of decline. When trust erodes, cooperation becomes harder, and the systems that require coordination begin to break down. Disease has also played a role in past collapses, and in a connected world, outbreaks can spread faster than ever before. While medical technology has advanced, it's not a guarantee of safety. New pathogens, resistance to existing treatments, or failures in health systems can create crises that overwhelm other parts of society. What makes the collapse of a civilization truly planetary in scope is when it pushes the environment beyond the conditions necessary for recovery. A society might collapse and be replaced by another if the environment remains stable enough to support it. But if the collapse involves damage to the biosphere, widespread deforestation, soil loss, mass extinctions, or a disrupted climate, then the planet itself becomes less capable of supporting future civilizations. That's when a world moves closer to joining the graveyard. From a broader perspective, civilizations are experiments in organizing intelligence and resources on a scale larger than any individual or community. The experiment has to balance ambition with restraint, growth with sustainability, and innovation with caution. If that balance tips too far in the wrong direction, collapse becomes more likely. And if collapse comes after the biosphere has been degraded, there may be no second chance. For other worlds, the same principles could apply. If intelligent life exists elsewhere, it may face the same pressures: resource limits, environmental changes, internal conflict, and the temptation to push technology faster than the ability to manage it. Civilizations that fail to navigate these pressures may disappear, leaving behind a planet that no longer supports complex life. From a distance, these worlds might look as if nothing ever happened, their surfaces weathered by time until any trace of cities or technology is gone. This possibility feeds into the larger question we've been following all along. If Earth is one of many attempts at a living world, how many others have reached the point of building civilizations only to lose them? And if the answer is many, then the silence we hear from the stars may not be from worlds that never lived, but from worlds that lived, advanced, and then fell. From here, the focus turns to the other kind of collapse, the kind that isn't caused by the society itself but by the star that gives it life. Because no matter how well a planet manages its resources or how stable its systems are, it still lives under the long shadow of the star it orbits. If Earth teaches us anything about survival, it's that luck has been just as important as resilience. The story of our planet isn't just one of stable conditions and careful balances, it's also a story of near misses, of events that could have ended the experiment long before we ever arrived. These close calls are the reason we can even sit here and talk about the fragility of worlds. Without them breaking in our favour, we'd be another quiet rock in the cosmic graveyard. Some of these escapes happened long before humans existed, in a time when life was still microscopic. Billions of years ago, the young sun was dimmer than it is today, faint enough that, by all logic, Earth's surface should have been frozen solid. Yet somehow, the planet stayed warm enough for liquid water. This faint young sun paradox is still debated, but it likely involved a combination of greenhouse gases and geological activity that trapped enough heat to keep the oceans from turning to ice. If Earth hadn't managed that balance, life might never have gained a foothold at all. Then there's the matter of impacts. The early solar system was a shooting gallery, with asteroids and comets striking planets regularly. Many of these collisions were devastating, and some could have completely reset the clock on life's progress. One especially massive impact, the one that formed our moon, happened before life began. Had it occurred later, it might have sterilized the planet. Even after the worst of the bombardment ended, dangerous impact still happened. The asteroid that wiped out the dinosaurs 66 million years ago was large enough to destroy much of Earth's life, but it didn't go quite far enough to finish the job. Had it been a little larger, or struck at a different location, recovery might have been impossible. Volcanism has also pushed us close to the edge. The Siberian Traps eruptions 252 million years ago triggered the deadliest extinction in Earth's history, wiping out around 90% of marine species. The planet took millions of years to recover. That we did recover at all was partly down to timing and partly down to the planet's ability to eventually restabilize its climate. In a less favourable scenario, volcanic gases might have driven a permanent runaway greenhouse effect, like what happened on Venus. Ice ages have tested the planet more than once, but the snowball Earth events of roughly 700 million years ago were among the most extreme. Glaciers reached the equator, and the oceans may have been covered in ice for millions of years. Life clung on in pockets, perhaps near hydrothermal vents, or under thin layers of ice where sunlight could still reach. If those refugees hadn't existed, global photosynthesis might have collapsed, and with it the oxygen supply that later complex life would depend on. There have also been near misses that are less dramatic but still consequential. The stability of Earth's axial tilt, for example, is largely thanks to our unusually large moon. Without it, the tilt could have swung wildly over time, leading to extreme and unpredictable climate shifts. Mars, which lacks such a stabilizing moon, has experienced these kinds of swings, and its climate has been far less stable as a result. The moon's stabilizing influence has been a quiet, constant safeguard for billions of years. Our planet's magnetic field is another shield we might take for granted. Generated by the movement of molten iron in the outer core, it deflects much of the solar wind that would otherwise strip away our atmosphere. Mars once had a magnetic field but lost it, and with it much of its air and water. Earth's field has weakened and reversed many times in the past, but it's never collapsed entirely during the age of life. If it had, we might be living on a far harsher, drier, and more barren planet, if we were living here at all. Even biological events have brought us close to losing it all. The Great Oxidation Event, driven by photosynthetic microbes more than 2 billion years ago, transformed the atmosphere in a way that was toxic to much of the existing life. Earth came close to an extinction event so deep it could have reset the biosphere entirely. That life not only survived but eventually adapted to oxygen was another lucky break, one that set the stage for the kind of metabolism complex organisms depend on. As humans, we've had our own brushes with catastrophe, though most of them are harder to detect in the deep past. Massive volcanic eruptions, such as the Toba supereruption around 74,000 years ago, may have reduced the human population to a fraction of its former size. Ice Age climate shifts forced migrations and bottlenecks that could have ended differently if conditions had been just a little harsher. Even in recorded history, outbreaks of disease, widespread famine and conflict have threatened large parts of the population, though never on a truly global species-ending scale. Yet, the thread through all of this is that survival often comes down to a mix of factors we can't control and a few we can. Geological processes, orbital mechanics, and stellar behaviour operate far beyond human influence. But how life responds, whether by adapting, finding refuges, or changing the environment in its favour, determines whether a close call becomes a final one. What makes Earth's narrow escapes so striking is how each one could have gone the other way. A slightly different trajectory for an asteroid, a few more centuries of volcanic activity, a marginally weaker magnetic field. Any of these could have rewritten the story entirely. In the grand sweep of planetary history, small changes can make the difference between a biosphere that thrives for billions of years and one that ends abruptly. From the perspective of the graveyard of worlds, these escapes are rare. For every planet that manages them, many more fail. Some never recover from a single blow. Others suffer a series of smaller hits that, over time, erode their habitability beyond repair. Earth's survival so far doesn't guarantee it will continue, but it does mean we've been given a rare opportunity, one that most worlds never get. The real question is what we do with that opportunity. Narrow escapes can be warnings as much as they are blessings. Each one says, in its own way, that we are not invincible, that the stability we enjoy is built on contingencies and coincidences. Ignoring that is a risk in itself, because while we can't prevent every danger, we can prepare for some. And the more we learn about the fates of other worlds, the more we can see where preparation might matter most. From here, it makes sense to turn our attention outward again, to the planets that never got their own narrow escapes, and what their fates can tell us about how rare it is to keep winning against the odds. If we try to trace the path of Earth's survival from its formation to today, it doesn't follow the clean, predictable line we might want it to. Instead, it's a twisting route full of sudden changes, unlikely outcomes, and moments where things could just as easily have gone the other way. That's the role of chance, the part of a planet's history that can't be forecast with perfect accuracy, no matter how much science we throw at it. Alongside that is chaos, not just in the sense of destruction, but in the mathematical sense. Small changes at one point leading to vastly different outcomes down the line. Together, they shape the destiny of worlds in ways that no amount of planning or stability can entirely override. Chance is easy enough to understand in everyday terms. It's the roll of the dice that determines whether an asteroid misses or strikes. It's whether a planet forms with just enough iron in its core to sustain a magnetic field for billions of years, or whether it cools too fast and loses that shield. It's whether plate tectonics begin in time to regulate the climate, or whether the crust locks up too early and lets the atmosphere spiral out of balance. These are the cosmic equivalents of coin flips, and a planet's habitability depends on how often they land the right way. Chaos is subtler. It's not about one-off events, but about systems where tiny variations in initial conditions lead to huge differences over time. The orbits of planets, for example, are influenced by countless gravitational tugs from their neighbours. Over millions or billions of years, those tugs can shift a planet's path just enough to alter its climate, its seasons, or even whether it remains in the habitable zone. Climate systems themselves are chaotic in this way. A slight change in atmospheric composition, ocean currents, or solar output can tip them into new patterns that are difficult to reverse. On Earth, the interplay of chance and chaos has been constant. The asteroid that ended the dinosaurs' reign might have missed by a few thousand kilometres if its timing had been slightly different. The Toba supereruption could have coincided with other environmental stresses in a way that made recovery impossible. The faint young sun paradox might have gone unsolved if volcanic activity had been just a little weaker, leaving Earth frozen for billions of years. In each case, the variables are so tightly linked that small differences in one area ripple through the whole system. Other planets show us how different these ripples can be. Mars likely lost its magnetic field early on, which allowed the solar wind to strip away its atmosphere. That might have been the result of its smaller size, its cooling rate, or the specifics of its internal chemistry, factors determined during formation and then shaped by the randomness of collisions in the early solar system. Venus may have been close to Earth in its early conditions, but slight differences in rotation, solar exposure, or volcanic outgassing may have set it on a path toward runaway heating instead of stability. In both cases, the differences were small at the start but decisive in the end. This is why the concept of a habitable zone is so much more complicated than a simple band of distances from a star. A planet can sit in the middle of that zone and still be uninhabitable if chance and chaos conspire against it. The reverse is also true. Some worlds may survive outside the classic habitable zone, thanks to factors like thick atmospheres or internal heating. What matters is the trajectory the planet takes, and that trajectory is sensitive to countless small influences. When scientists model the evolution of planetary systems, they often run simulations hundreds or thousands of times with slightly different starting conditions. The results can vary wildly, even when the changes are tiny. That's chaos at work. And in the real universe, there's no reset button. The path a planet takes is the only one it gets. If it drifts toward uninhabitability, it may never come back. For life, this means that stability isn't just about being in the right place at the right time. It's about surviving the unpredictable twists along the way. On Earth, life has done this by being flexible, finding ways to live in extreme environments, rebounding after extinctions, and exploiting new opportunities when they appear. But even flexibility has limits. There are thresholds beyond which adaptation isn't possible, and those thresholds can be crossed suddenly if chance and chaos align in the wrong way. From the perspective of the graveyard of worlds, chance and chaos are the silent sculptors of planetary history. They determine how often promising beginnings turn into lasting success, and how often they end in failure. They're also the reason we can't expect to find many planets that are exact copies of Earth. Even if two planets start with nearly identical conditions, their paths will diverge over time, shaped by random impacts, orbital shifts, and the feedback loops in their climates and geology. By the time billions of years have passed, their surfaces may have nothing in common. This unpredictability complicates our search for life. We can identify planets in habitable zones, measure their sizes and orbits, and even analyze their atmospheres for hints of biological activity, but we can't know their full histories without detailed exploration. A planet might look perfect from light years away, only for a closer look to reveal that it suffered an extinction event or a slow, environmental collapse centuries or millennia ago. The signs of that loss might be faint, buried under layers of dust, ice, or volcanic ash. There's also the possibility that chance and chaos could favour life in ways we haven't yet imagined. An impact that destroys one ecosystem could create conditions for another to thrive. A slight wobble in a planet's orbit could drive seasonal changes that encourage biodiversity. Even catastrophic events can sometimes open new evolutionary paths, as they have on Earth. The same forces that can end life can also reshape it in ways that make it more resilient. The outcome depends on the balance between destruction and opportunity, a balance that shifts unpredictably over time. The reality is that no planet, no matter how stable it seems, is entirely safe from the influence of chance and chaos. The same is true for civilizations. We can manage risks, build redundancies, and try to predict threats. But we can't eliminate randomness from the equation. The best we can do is prepare for a range of possibilities, knowing that the exact one we'll face might be something we never thought to expect. In the bigger picture, This understanding reinforces just how rare and fragile long-term habitability is. Most planets won't get the combination of lucky breaks and manageable challenges that Earth has had so far, and even here, the game is still ongoing. The next draw from the deck could be a harmless fluctuation, or it could be the beginning of a chain of events that shifts the planet into a very different state. From here, the focus naturally turns to how we look for signs of life in the middle of all this unpredictability. How we can tell the difference between a planet that's thriving and one that's coasting on the last remnants of better days, and how we might spot worlds that beat the odds in ways we've yet to witness. If there's one thing the universe seems to dislike, it's waste. Matter, energy, and even the building blocks of life itself are constantly being used, broken down and reassembled into something new. Stars burn out, but their ashes seed the next generation of stars and planets. Planets are shattered, but their fragments may end up forming moons or being swept into other worlds. Even the bodies of the living things are dismantled and reused, atom by atom, long after the organisms themselves are gone. In that sense, the universe is a recycling centre, on a scale so vast that entire civilizations could rise and fall within a single cycle, without ever realising they were part of it. For planets, this recycling is built into their very existence. The elements that make up Earth, the iron in its core, the silicon in its crust, the carbon in its air and life, were forged in earlier stars. Some of those stars ended quietly, shedding their outer layers into space. Others ended violently, exploding as supernovae and flinging their contents across light years. Over millions of years, these scattered materials were drawn together by gravity, eventually forming new systems. Our Sun is one of those second-generation stars, and our planet is made from the debris of earlier worlds that no longer exist in any recognizable form. This means that every planet, every asteroid, and every moon is, in some sense, a collection of leftovers. And the recycling doesn't stop at their formation. Geological activity constantly reworks a planet's surface, erasing old features and creating new ones. Erosion grinds down mountains into sediment, which is later uplifted into mountains again. Volcanic eruptions bring material from deep within the planet to the surface, where it can be weathered and incorporated into soil. Even the atmosphere is recycled, with gases entering and leaving it through natural cycles like volcanism, respiration, and photosynthesis. On Earth, this recycling has been crucial for maintaining habitability. The carbon cycle, for example, regulates the planet's temperature over long timescales. Carbon dioxide is removed from the atmosphere through processes like weathering, and stored in rocks, then released again through volcanic activity. Without this cycle, Earth could have drifted into a permanent ice age or a runaway greenhouse state. In that sense, recycling is not just a feature of the planet, it's one of the reasons it's still alive. When life enters the picture, recycling takes on another layer. Living organisms don't just adapt to their environments, they alter them in ways that affect the recycling of materials. Plants take in carbon dioxide and release oxygen. Animals breathe oxygen and release carbon dioxide. Decomposers break down dead organisms, returning nutrients to the soil and water. Over time, these processes become intertwined with geological cycles, creating a system in which life and planets sustain each other. But this recycling isn't always gentle or continuous. Sometimes it's triggered by catastrophic events. An asteroid impact can vaporize rock, throw debris into the atmosphere, and redistribute material across the globe. A massive volcanic eruption can bury landscapes under lava, altering the flow of rivers and reshaping coastlines. These events destroy ecosystems, but they also create opportunities for new ones. The land left behind by a retreating glacier, for example, is barren at first, but eventually becomes home to plants, animals, and entire communities. In this way, destruction and creation are part of the same cycle. Beyond individual planets, recycling operates on stellar and galactic scales. The Milky Way is full of giant molecular clouds. regions of gas and dust where new stars and planets are born. These clouds are fed by the remains of older stars and systems. Supernova remnants, planetary nebulae, and the steady outflow of matter from aging stars all contribute material to these clouds. Over millions of years, gravity pulls the material together, igniting new stars and starting the cycle again. Every new planet that forms is in effect a blend of countless older ones. Even black holes, which seem like the ultimate endpoints, play a role in cosmic recycling. While the matter they consume is lost to us in its original form, their influence on their surroundings, through gravity, radiation and the jets they produce, can trigger the formation of new stars and structures. In this way, even the most extreme objects in the universe are part of the process. From the perspective of the graveyard of worlds, recycling means that no failure is entirely final. A planet that loses its habitability might be broken apart by impacts, its fragments becoming part of other worlds. Its atmosphere might be stripped away, with the gases joining the interstellar medium and contributing to future planets. Its water might freeze, sublimate, and eventually be carried elsewhere. The materials that once supported life can support it again, just not in the same place or in the same form. For civilizations, this can be a sobering thought. The metals we use to build technology were forged in ancient stars and recycled through countless other worlds before arriving here. The oxygen we breathe has been through innumerable life cycles. Even the hydrogen in the water we drink has been part of the universe since the first minutes after the Big Bang. In a very literal sense, we are made of recycled materials, and so is everything we build. This also means that when we look for life elsewhere, we're looking for the right combination of recycled parts. A planet doesn't need to be made from anything exotic, just the same carbon, oxygen, nitrogen and other elements that have been part of the cosmic inventory for billions of years. What matters is how those parts are arranged, and whether they end up in a system that can sustain them in the right conditions for long enough. Recycling also plays a role in the end stages of civilizations. If a society collapses, its materials, metals, ceramics, plastics, will eventually break down and re-enter the planet's cycles, though on very different timescales. In geological terms, the ruins of cities might be reduced to sediment in a fraction of the planet's lifespan. What remains might be incorporated into new rock layers, becoming part of the geological record for any future explorers to find. Even if no one ever does, the material will still be part of the planet's ongoing transformation. In a way, this makes the universe's recycling system both a comfort and a warning. It means nothing is truly lost, but it also means nothing is guaranteed to last in its current form. Planets, civilizations, and even stars are temporary arrangements of matter and energy, destined to be broken down and reused in ways that may have nothing to do with their original purpose. The fact that Earth is currently in a form that supports us is a temporary state in a process that has been going on for billions of years and will continue for billions more. The recycling of the universe doesn't favour life or oppose it, it simply operates. Whether life benefits from it depends on timing and circumstance. A planet might form from recycled materials in a region of space where conditions are perfect for habitability, or it might form in a place where those conditions never come together. From our point of view, the process is impartial, even indifferent. From the point of view of the universe, it's simply the way things work. This perspective can make our own situation feel both fragile and deeply connected. We are part of a chain that stretches back to the first atoms, and we are contributing to the chain that will stretch forward long after we're gone. Our existence depends on the survival of certain cycles, but it also depends on the fact that nothing in the universe stays exactly as it is forever. In that sense, every world, whether it's thriving or dead, is part of the same ongoing transformation. And if Earth is one of many failed or successful worlds, then in the long run, its materials will feed into something else. Another planet, another star, another potential home for life. From the graveyard's perspective, failure isn't permanent. It's just another stage in the process. What matters is what happens while a world is still intact, still able to support the complexity we call life. From here, the story turns to how we use this knowledge in our search for life, how understanding the cycles of creation and destruction helps us decide where to look, what to expect, and how to interpret the silence we so often hear in return. When we talk about the graveyard of worlds, it's easy to think of it as a gallery of silence, a place where planets sit inert, their stories over. But in reality, the dead worlds are not silent. They are archives. Every scar, every layer of rock, every trapped pocket of ancient atmosphere is a page in a record that spans billions of years. And those records are invaluable. They can't tell us everything, but they can show us patterns, reveal the processes that lead to failure, and give us the context we need to understand our own fragile position in the universe. The first lesson they offer is that habitability is a moving target. Mars, with its ancient riverbeds and mineral deposits formed in water, shows us that a planet can start warm and wet and still end up frozen and barren. Venus, with its crushing atmosphere and oven-like surface, shows us the opposite. A place that may have been mild in its youth, but tipped into a runaway greenhouse that made it lethal to any life we can imagine. Neither planet sits in a static state. Each one changed dramatically over time, and neither change was in the direction of greater habitability. This tells us that it's not enough for a planet to be in the right place, in its star's habitable zone. That's just the starting point. The real challenge is keeping the conditions stable for the billions of years it can take for complex life to emerge. A slight change in atmosphere, a shift in volcanic activity, or the loss of a magnetic field can send a planet drifting out of that narrow window, sometimes permanently. The second lesson is that mass extinction is not rare. On Earth, we tend to focus on the Big Five, the most dramatic and widespread extinction events in our planet's history. But the fossil record shows many smaller die-offs in between, triggered by everything from changing sea levels to regional volcanic events. If our planet, with all its apparent advantages, has faced so many near resets, it's not hard to imagine that other worlds have faced even more. Some might never have recovered. Third, the dead worlds remind us that catastrophes can be both sudden and slow. An asteroid impact delivers devastation in seconds, but the long-term collapse of a planet's atmosphere can be just as deadly. A biosphere can wither over millions of years without a single dramatic moment to mark its turning point. This is important for how we search for life. A planet might appear stable today but be in the middle of a long decline. Without understanding the rate and direction of its changes, we might mistake it for a permanent oasis when it's actually halfway to the graveyard. Fourth, they show us the limits of adaptation. Life is resilient, but it's not indestructible. There are thresholds that, once crossed, even the hardiest organisms can't survive. On Mars, if life ever existed on the surface, it couldn't adapt to the loss of atmosphere and the bombardment of radiation that followed. On Venus, if life once thrived in oceans, it couldn't survive the runaway heat and pressure. Studying these thresholds helps us understand not just where life can live, but where it can't, and how close Earth might be to its own boundaries. Fifth, they teach us that survival is sometimes a matter of timing. If the asteroid that killed the dinosaurs had arrived a few million years earlier or later, it might have struck a planet in a very different ecological state, with a very different outcome. If Mars had held onto its magnetic field a little longer, life might have had time to gain a foothold strong enough to endure. Timing doesn't just shape the history of one world, it shapes the chances of life emerging in the first place. Another lesson, perhaps the hardest one, is that intelligence is not necessarily the answer. We often think of technological civilizations as the ultimate expression of a planet's potential, the point at which life can begin to defend itself against natural threats. And while that's true in some respects, civilizations also create their own vulnerabilities. A dead world might have ended not because it couldn't survive the cosmos, but because it couldn't survive itself, if any such worlds exist. And given the scale of the galaxy, it would be strange if they didn't. then their ruins would be among the most haunting lessons in the graveyard. We also learn from the dead that nothing is truly isolated. The fate of a planet is tied to its star, its neighbouring worlds, its place in the galaxy, and the vast cycles of matter and energy that flow through the universe. A nearby supernova can strip a planet's atmosphere. A shift in a giant planet's orbit can destabilise smaller worlds. Even the passage of a star through a dense region of interstellar space can alter the conditions for life. Dead worlds remind us that survival is never entirely under a planet's own control, and perhaps most importantly, they teach us humility. It's tempting to think of Earth's history as inevitable, as though life here was destined to reach this point. But the graveyard shows us that there's nothing inevitable about it. The universe has no shortage of promising starts that ended in silence. The fact that we've avoided that fate so far is the result of a chain of events so specific and so contingent on chance that it's almost impossible to replicate. That's not to say it can't happen elsewhere, only that it will be rare when it does. From a scientific standpoint, the dead worlds are not just cautionary tales, but research opportunities. By studying Mars, Venus, and the moons of the outer planets, we learn more about how atmospheres evolve, how climates shift, and how geological processes can support or undermine habitability. Missions that map the surface of these worlds, analyse their compositions, and probe their histories give us more than just a better picture of their pasts. They give us a better sense of Earth's possible futures. Even without visiting them, we can study exoplanets that show signs of being past their prime. Some may have unusual atmospheric compositions that hint at a collapse in climate stability. Others might orbit stars that have already begun to shift into less favourable states. By cataloguing these cases, we can begin to map out the boundaries of long-term habitability and understand which conditions are most likely to persist. This kind of knowledge isn't abstract. It has practical implications for our own survival. If we can identify the early warning signs of decline in other worlds, we might recognise them in our own before it's too late. If we can see how other planets lost their stability, we might find ways to avoid the same fate. The dead worlds are reminders that we're part of a much larger pattern, and that our survival depends on understanding it. But there's another kind of lesson here, one that's less about science and more about perspective. Dead worlds tell us that life is precious not because it's common, but because it's rare. They remind us that every generation living on a thriving planet is inheriting a gift that countless other worlds have lost. They tell us that the graveyard is vast, but not universal, and that being among the living is an extraordinary position to be in. The challenge, of course, is what we do with that position. If we treat our survival as inevitable, we may end up as just another case study in the graveyard's archive. If we treat it as fragile, we may take the steps needed to extend it. The dead worlds can't tell us which path to take, but they make it clear which outcomes are possible. From here, the path forward is to consider how we detect life and loss in the wider galaxy, how the signals we search for can tell us whether a world is thriving, fading, or already gone, and how those signals might be hiding in plain sight among the stars we've already catalogued. It's easy, living day to day, to imagine that the conditions we see around us are fixed. The air we breathe, the climate we've adapted to, the ecosystems we rely on, they feel like permanent features of the planet. We grow up inside them, build our homes and cities within them, and treat them as a given. But the truth is that everything about Earth's current state is temporary. This moment in geological and biological history is as fragile as a bubble, held together by forces that have shifted in the past and will shift again. Our present is a narrow window, balanced between extremes, and it can close without much warning. From a planetary perspective, we are living in an unusually stable climate. Over the past 10,000 years, temperatures and sea levels have stayed within a range narrow enough to allow agriculture to develop, cities to be built, and civilizations to spread across the globe. That stability is the foundation of everything we recognize as modern life. Before it, the climate was more volatile, swinging between ice ages and warmer periods. After it, the climate will inevitably change again, either through natural cycles or through human influence. The conditions we're in now are not the planet's default state, they are an exception. This stability is the result of a combination of factors that have, for the moment, lined up in our favour. The tilt of Earth's axis is steady enough to keep seasonal shifts predictable. The atmosphere is thick enough to hold warmth, but not so thick as to trap too much of it. The oceans circulate heat around the globe in patterns that keep extreme temperatures from dominating most regions. Volcanic activity is low compared to some points in the past, and the sun's output is relatively stable. None of these factors are fixed in place forever. Each has changed before, and each will change again. When we look at other worlds, we see how fragile such alignments are. Mars lost its magnetic field, and with it, its ability to shield its atmosphere from the solar wind. Venus may have once had oceans, but a combination of solar heating and atmospheric changes pushed it into a runaway greenhouse effect. Even small shifts in a planet's environment can set off feedback loops that amplify those changes, making recovery difficult or impossible. On Earth, feedback loops exist as well. Melting ice reduces the planet's reflectivity, causing more heat to be absorbed, which melts more ice. Thawing permafrost releases greenhouse gases, which warm the atmosphere further. The destruction of forests reduces the planet's ability to absorb carbon dioxide, which accelerates warming. These loops can be triggered by natural changes, but they can also be triggered or accelerated by human activity. This is where the fragility of the present moment becomes most apparent. We're now in a position where we can alter the planet's climate faster than natural processes can balance it. In geological terms, the changes we're making are abrupt. A spike in greenhouse gas levels in just a few centuries, shifts in land use and biodiversity in a matter of decades. The Earth system is resilient, but it is not invulnerable. Push it far enough, and it will shift into a new state, one that may not be compatible with the civilization we've built. And this fragility isn't limited to climate. Our global food systems depend on consistent weather patterns, predictable rainfall and fertile soils. Our freshwater supplies depend on glaciers, snowpack and stable river flows. Our infrastructure is built to withstand certain ranges of temperature, wind and flooding. A significant shift in any of these could disrupt the networks that sustain billions of people. The more interconnected our systems become, the more a failure in one area can cascade into others. Technology gives us tools to manage some of these risks, but it also creates new ones. Our dependence on complex globalized supply chains means that disruptions in one region can ripple worldwide. Our reliance on digital systems makes us vulnerable to failures in power grids, communications, or cybersecurity. Even advances intended to protect us, like genetic engineering or artificial intelligence, come with the possibility of unintended consequences that are difficult to foresee or control. From a longer-term perspective, even forces far beyond our control can alter our present moment. A large volcanic eruption could inject enough particles into the atmosphere to cool the planet for years, disrupting agriculture. An asteroid impact, though rare, could cause global devastation in days. Changes in the sun's activity could shift climate patterns in ways we are not prepared for. These events have happened before in Earth's history, and they will happen again. The question is whether we will face them from a position of stability or instability. When you think about the graveyard of worlds, you realize that every one of them had a present moment at some point in its history, a time when conditions were good enough for life to flourish. On some, that moment may have lasted millions of years, on others, only a few thousand. The duration doesn't matter to the outcome. Once the moment ends, it rarely returns in the same form. The loss might be gradual, or it might be sudden, but it's almost always irreversible on human timescales. The fragility of our present is not meant to inspire despair, but awareness. The fact that we live in a rare, stable period should not make us complacent. It should make us careful. We have the ability to recognize warning signs, to model potential changes, and to take actions that can extend the lifespan of our current conditions. That's not something most planets get. In the graveyard, worlds don't get to see their decline coming. They don't get to debate what to do about it. They simply follow the trajectory their conditions dictate. But awareness is only useful if it's acted upon. Recognizing fragility is one step. Building resilience is the next. That means protecting the systems we depend on, reducing the pressures we place on the environment, and preparing for disruptions that will inevitably come. It also means accepting that some changes are unavoidable, and that adapting to them is as important as trying to prevent them. In the larger cosmic context, our present moment is a blip, but for us, it's everything. It's the time we have to decide whether we'll join the worlds in the graveyard sooner than we have to, or whether we'll stretch this rare period for as long as possible. That choice is still ours to make, but only if we remember how easily the conditions we rely on can be lost. From here, it makes sense to shift focus to how we read the signs. The clues that tell us whether a world is thriving, declining, or already silent, and how those signs might be far subtler than we expect when we look out into the galaxy. When we describe Earth as being in the Goldilocks zone, we mean that it sits at just the right distance from the Sun, not too hot, not too cold, for liquid water to exist on its surface. It's an appealingly simple idea, and it has been one of the guiding concepts in the search for life elsewhere. But the more we study planets, the more we realise that this idea of just right is far more complicated than the neat diagram in a textbook. Being the right distance from a star is only the beginning. Staying just right is an ongoing challenge, and in many cases it's a challenge most worlds lose. The Goldilocks problem starts with the fact that the habitable zone itself is not fixed. Stars change over time, gradually increasing in brightness as they age. A planet that is comfortably within the habitable zone today might find itself on the inner edge in a few 100 million years, with rising temperatures pushing it toward a greenhouse state. Likewise, a planet near the outer edge might slip into a permanent freeze if its star's output decreases or if its atmosphere thins. This means that habitability is not a permanent feature. It's a moving window that a planet has to stay within, sometimes against long odds. Then there's the role of atmosphere. Without a thick enough atmosphere to trap heat, even a planet squarely in the habitable zone will be too cold for liquid water. Mars is the obvious example. It orbits within the outer region of the Sun's habitable zone, but its thin atmosphere can't hold enough warmth, leaving it frozen most of the time. On the other hand, too thick an atmosphere can trap so much heat that a planet turns into an oven, as happened with Venus. The just right balance is a narrow range, and it depends not only on initial conditions, but on how the planet's climate and geology interact over billions of years. Geology plays a role that's often overlooked in casual discussions of habitability. A planet's internal heat drives volcanic activity, which in turn releases gases into the atmosphere. Plate tectonics can regulate climate by recycling carbon between the surface and the mantle. Without these processes, a planet might lose its atmosphere, or it might let greenhouse gases build up to dangerous levels. Earth has benefited from this geological thermostat for most of its history, but there's no guarantee that such a system will operate on every planet in the habitable zone. Water, the ingredient we often treat as the defining requirement for life, brings its own complications. Too much water, and a planet might end up with a global ocean and no land, limiting the cycling of nutrients between the ocean and atmosphere. Too little, and life may never get the chance to start at all. Even the distribution of water matters. A planet might have polar ice caps and equatorial deserts, or it might be locked in ice with only pockets of liquid water deep underground. The presence of water alone doesn't make a planet just right. How that water interacts with the rest of the planet's systems is what counts. The Goldilocks problem becomes even more tangled when you consider external influences. Large moons can stabilize a planet's axial tilt, reducing extreme climate shifts, while the absence of such a moon can make the climate swing wildly over time. The presence of giant planets in the same system can protect smaller worlds from frequent asteroid impacts by deflecting debris, but they can also destabilize orbits if their gravitational influence is too strong. Even the galaxy itself plays a role. Planets closer to the galactic center might be exposed to more radiation from nearby supernovae, while those farther out might have fewer heavy elements to build rocky planets in the first place. From what we've learned so far, most planets don't manage to hit the just right combination of all these factors. Many are too small to hold an atmosphere, too geologically inactive to regulate climate, too unstable in their orbits, or too unlucky with their star's evolution. And even those that start out with favourable conditions may not keep them. The Goldilocks state is not a destination a planet reaches and stays at forever. It's a balance that has to be maintained, and the universe is constantly trying to knock that balance off centre. This has direct implications for our search for life. When astronomers identify an exoplanet in its star's habitable zone, it's a good starting point, but it's not a guarantee of anything. To know whether a world is truly just right, we'd need to know its atmospheric composition, its geological activity, its water distribution, its orbital stability, and how all of those factors have changed over time. Without that information, the habitable zone is more of a hopeful label than a definitive assessment. There's also a time element to the Goldilocks problem. Life, at least as we know it, takes time to become complex enough to build ecosystems, let alone civilizations. A planet might pass through a habitable phase too quickly for complex life to develop before conditions change. Or it might spend billions of years in a stable state, only for something, a change in its star's output, a shift in its atmosphere, a massive impact, to end that stability before intelligence has time to arise. Earth's own history shows how close we may have come to missing our window entirely. When you step back and look at the bigger picture, the Goldilocks problem reveals itself as not just a matter of location, but of persistence. Being just right is rare not just because the requirements are narrow, but because maintaining them over billions of years requires a planet to navigate a gauntlet of potential failures. In the graveyard of worlds, there are likely many planets that were briefly perfect, only to slip away before life had the chance to fully take hold. This is why Earth's position is so precarious and so remarkable at the same time. We have been in the habitable zone for billions of years, and our planet systems have worked together, sometimes by luck, sometimes by feedback, to keep conditions within that narrow range. We've survived impacts, ice ages, and massive volcanic events without tipping into a permanent uninhabitable state. That doesn't mean we always will, but it does mean we've managed to maintain the balance, longer than many worlds ever get the chance to. In a way, the Goldilocks problem is a reminder of how easy it is for a planet to fail. It doesn't take a total collapse of all systems, it only takes one key factor drifting out of balance. The temperature doesn't need to rise to the level of Venus or drop to the level of Mars. Even smaller shifts can trigger changes that make the planet less and less friendly to life. In that sense, habitability isn't an on-off switch, but a spectrum, and it can slide in the wrong direction gradually or suddenly. The more we understand about the Goldilocks problem, the more we realise that the conditions we enjoy now are both rare and temporary. The habitable zone will move, our atmosphere will change, the balance that keeps our climate stable will be tested again and again. We can try to influence the outcome, but we can't stop the larger forces at play. All we can do is work within the time we have, using the knowledge we've gained from other worlds to keep our own in that narrow, shifting space between too hot and too cold, too dry and too wet, too unstable and too static. And that leads naturally into the question of what we can actually do with that knowledge. Whether understanding the fragility of habitability and the forces that shape it can help us tilt the odds in our favour, or whether we are simply another world waiting our turn in the graveyard. When we look at the graveyard of worlds and the narrow conditions needed to avoid joining it, it's tempting to think of ourselves as the lucky exception, the planet that beat the odds, that found the right balance, that managed to stay, just right long enough for intelligent life to emerge. And in many ways that's true. Earth's history is a chain of improbable events, each one linking to the next in a sequence that, if broken at almost any point, might have left us with nothing more complex than microbial mats in shallow seas. But the question we can't escape is whether being an exception now means we will stay one. Every world in the graveyard was once the lucky one in its own way. Mars had its rivers. Venus may have had oceans. Other planets orbiting other stars may have gone through periods of stability that made them seem destined for longevity. None of them kept it. The difference between being the exception and being the next in line is not the starting conditions. It's whether you can maintain them when the universe inevitably begins to push back. When we talk about the odds, it's important to remember that they are not fixed. Earth's survival so far doesn't guarantee its future survival, just as past stability doesn't mean we're immune to sudden shifts. We are still subject to the same forces that reshaped Mars and Venus, the same potential catastrophes that can wipe out entire ecosystems, the same slow drifts toward instability that can make a planet unrecognizable over geological timescales. The only difference is that we're aware of them, and that awareness could, in theory, allow us to prepare. That awareness is a double-edged sword. On one side, it gives us the chance to avoid certain fates. We can track asteroids, monitor solar activity, model climate change, and develop technologies to mitigate or adapt to those threats. On the other, it introduces risks that no other species has faced before. We have the ability to alter the planet's atmosphere on a scale that rivals natural processes, to trigger mass extinction events through habitat destruction, to change the chemistry of oceans, and to unleash weapons capable of ending civilization in days. Our intelligence, the trait that sets us apart, is also the trait that could put us in the graveyard faster than any asteroid. If we want to know whether we're the exception or the next in line, one way to approach it is by looking at patterns. Civilizations, at least on Earth, have a tendency to grow until they stress the systems that support them. In the past, those systems were local: soil, fertility, fresh water, forests, fisheries. Now, they are global. The atmosphere, the oceans, the biodiversity of the planet itself, these are the foundations we depend on, and we're drawing them down at a rate that would be unsustainable, even without the added pressures of a changing climate. In that sense, the graveyard may not just be a collection of natural failures. It could also be a record of civilizations that crossed thresholds they didn't recognize or didn't act on in time. We don't yet have direct evidence of such civilizations elsewhere, but statistically it would be surprising if none existed. If life is common and intelligence arises even rarely, then there have likely been others before us who reached the point we're at now, aware of their fragility, capable of acting but not guaranteed to succeed. The danger is that we might assume we're different. It's easy to believe that our technology, our knowledge, and our ability to plan make us immune to the mistakes of the past. But those tools only work if we use them in time, and history suggests that recognizing a danger doesn't always lead to addressing it. Sometimes, the inertia of the systems we've built, the complexity of the problems we face, and the competing interests within our societies delay action until the damage is already irreversible. Of course, there's another way to look at the question. Maybe the very fact that we're having this conversation, that we can imagine the graveyard and see ourselves in it, means we have a chance to avoid it. No other species we know of has had the ability to model planetary-scale risks and deliberately alter their trajectory. If we are capable of anticipating the forces that could end our habitability and taking steps to counter them, then perhaps we can extend our time as an exception far beyond the average. That's a hopeful view, but it's not a guarantee. Being aware of a threat and acting effectively against it are two very different things, and there's no way to know whether the decisions we make now will have the intended result centuries or millennia from today. The timescales involved in planetary survival are so vast that even small miscalculations can have consequences long after anyone remembers why the decision was made. There's also the reality that some forces are beyond our control. We can't stop the sun from slowly brightening. We can't prevent a nearby star from going supernova. We can't halt the slow drift of continents or the eventual cooling of Earth's core. We can adapt to some of these changes, perhaps even use technology to offset them. But in the end, no world stays habitable forever. The question is not whether Earth will one day be in the graveyard, but when, and whether we'll be the ones who push it there sooner than necessary. If we imagine the graveyard not as a static place, but as a constantly expanding collection, then every living world is somewhere on the slope toward joining it. Some are near the top, freshly habitable and full of potential. Some are already sliding past the point where intervention could matter, and some, like us, are balanced on the edge, in a position where the next few centuries could determine which direction we go. From that perspective, the distinction between exception and next in line is less about identity and more about trajectory. It's not a label you get to keep permanently. It's a position you hold for as long as your planet's systems stay within the narrow bounds of habitability. The forces that could push us out of those bounds are always present, and whether they succeed depends on how we manage the balance between natural cycles and our own impacts. The unsettling truth is that we may not know the answer until it's too late. A tipping point might only be obvious in hindsight. A slow decline might feel like stability right up until it crosses a threshold. That's how many of the worlds in the graveyard probably ended. Not with a single catastrophic event, but with a series of changes that seemed manageable until they weren't. But that's also where the possibility lies. If we can detect those changes early enough, if we can understand the indicators of decline well enough, we might be able to act before they become irreversible. That requires more than technology. It requires the willingness to change how we live, to prioritize the long-term stability of the planet over the short-term momentum of growth. It's not an easy shift, and it's not one we've ever tried to make on a global scale before, but it may be the only way to remain the exception for longer than the average world manages. Whether we succeed or not will be part of the record someday, just as the stories of Mars, Venus, and the lifeless worlds we've never seen are part of theirs. If future explorers, human or otherwise, look back on Earth, they might see us as the rare example of a civilization that avoided the graveyard for far longer than expected. Or they might see us as yet another promising world that didn't recognize how close it was to the edge until it was already falling. From here, the focus turns naturally to the signals we might be leaving behind, the traces that could tell others whether we lasted or whether we joined the countless silent worlds that came before us. When we picture the graveyard of the worlds, it's easy to imagine it as a final resting place, a silent end where nothing more can happen. But the truth is, failure is rarely the end in the cosmic sense. A world that loses its habitability does not vanish. It remains part of the universe's ongoing machinery, its material still circulating, its energy still influencing its surroundings. Even in death, a planet has a role to play, and sometimes that role might set the stage for new beginnings elsewhere. Consider the debris of collisions. When a large asteroid or comet slams into a planet, the immediate effect might be devastation, but the long-term result can be redistribution. Fragments of rock, ice, and sometimes even organic molecules can be thrown into space. Some of those fragments might eventually land on other worlds, carrying with them the chemical seeds of life. On Earth, we found meteorites from Mars, pieces of another planet that made their way across tens of millions of kilometers to land here. If life ever existed on Mars, it's possible, though still unproven, that traces of it could have survived such a journey. That means a failed world might still contribute to the success of another. Even without collisions, failed worlds can influence their neighbours. A planet with a highly reflective surface might alter the light environment of nearby moons. A gas giant that drifts inward after forming could scatter other planets into new orbits, changing their climates in ways that make them more or less hospitable. Worlds are not isolated in their fates. They are part of a network of gravitational relationships that can reshape entire systems. Some failed worlds might remain useful long after losing surface habitability. A frozen planet far from its star could still have a subsurface ocean, kept liquid by the heat of radioactive decay or tidal forces from a nearby giant planet. If such an ocean exists, it might be a refuge for life even when the surface is sterile. In our own solar system, moons like Europa and Enceladus show that icy exteriors can hide active, possibly life-supporting environments. A world might be written off as dead from a distance, but still harbour something remarkable below. There's also the possibility of revival. While we tend to think of planetary habitability as a one-way decline, certain conditions could restore a world to a more favourable state. A frozen planet might thaw if its star brightens or if gravitational interactions pull it closer. A planet that has lost its atmosphere could slowly gain a new one from volcanic outgassing or from the impacts of volatile-rich comets. These processes are slow, measured in millions or billions of years, but the universe works on those timescales with ease. From a cosmic perspective, a few billion years in the graveyard might just be an intermission. For intelligent civilizations, failed worlds could become resources. A planet without life might be mined for its metals, tapped for its water, or used as a staging ground for further exploration. In that sense, failure from the standpoint of biology doesn't mean uselessness from the standpoint of technology. If we ever reach the point of travelling between stars, the graveyard might be less a place to mourn and more a map of potential outposts. But there's another, more speculative future for failed worlds, one that blurs the line between natural processes and deliberate action. If a civilization becomes advanced enough, it might be able to repair a planet's habitability. That could mean importing an atmosphere, redirecting comets for water, or building structures to control climate. These ideas, often filed under terraforming, are still far beyond our current capabilities, but they are not forbidden by the laws of physics. A failed world might not stay failed forever if someone decides to intervene. Of course, such interventions raise questions about ownership, ethics, and unintended consequences. Would reviving a planet that once had life interfere with whatever might have developed in its absence? Could a restored world remain stable for the long term, or would it simply slide back into the conditions that ended its habitability in the first place? The graveyard holds no answers to these questions, but it does hold the examples we'd need to think them through. There's also the legacy of a failed world to consider. Even after its surface becomes uninhabitable, its geological record remains. A planet that once had oceans, rivers or forests might preserve fossils, mineral deposits, or isotopic signatures that reveal its past. For future explorers, these records would be priceless, not just as scientific data, but as stories. A failed world could be a museum of its own history, offering insights into the possibilities and limits of life. In a way, the future of failed worlds mirrors the cycle of matter itself. Nothing is truly lost, it is transformed. A planet that can no longer support life becomes part of the raw material for something else. A moon, a ring system, a new planet forming in another star's nursery. The boundaries between living and dead worlds are less clear than we might think. Even the most barren rock drifting through interstellar space is a piece of the larger puzzle, carrying with it the history of its system and the potential to influence another. This perspective can shift how we think about our own planet's long-term future. When Earth eventually becomes uninhabitable, whether in hundreds of millions of years due to natural change or sooner due to human mismanagement, it won't simply vanish. Its atoms will scatter, some of them perhaps becoming part of new worlds. Its story will continue in forms we can't predict. The graveyard is not an end, it's a transition point. The idea that failed worlds still have futures also means that our search for life should not be limited to the obviously habitable. A planet that looks dead today might have been alive yesterday, and might be alive again tomorrow in cosmic terms. Studying it could give us the knowledge to help other worlds, including our own, stay habitable longer. The graveyard isn't just a warning, It's a library of solutions if we're willing to read it carefully. And maybe that's the most important point. The future of failed worlds depends on how we define failure. If we think of it strictly as the end of surface life, then yes, most worlds will fail eventually. But if we think of it as a change in state, part of a cycle that can lead to new forms and new opportunities, then no world is truly finished. It may no longer be what it was, but it will become something else, and in becoming something else, it remains part of the living universe. From here, it's only natural to look at the larger picture, not just what happens to individual worlds, but what the graveyard as a whole tells us about the life cycle of planets, and what that means for our understanding of the cosmos itself. When we step back far enough to see not just Earth, not just our solar system, but the sweep of worlds that have existed, flourished and gone silent, it becomes clear that the graveyard is not an anomaly. It is the rule. The number of planets that are still alive, still holding on to the fragile balance of conditions that allow life to persist, is almost certainly far smaller than the number that have already lost it. That doesn't make the living ones less remarkable. It makes them more so. In the face of that reality, our place is both humbling and precarious. We are perched in a rare moment of stability on a world that, by cosmic standards, is still young but already tested. We've survived asteroid impacts, climate swings and mass extinctions. We've developed the ability to understand our planet's history, to model its future, and to see our own vulnerability. But we've also created new risks that no natural process would have imposed. Risks that could undo our stability faster than the universe ever would have on its own. The graveyard is a reminder that no planet, no matter how fortunate, can avoid change forever. Stars evolve, orbits shift, atmospheres leak away or thicken beyond tolerance. Worlds cool or heat or get remade by collisions. Some of those changes happen slowly enough for life to adapt. Others happen too fast for adaptation to keep up. The difference between a thriving world and a failed one is not where the change happens, but how well the systems in place can respond to it. For us, those systems are no longer just natural. We have added human-made layers to the planetary equation, layers that can help or harm depending on how they're managed. Our technology can track incoming threats, repair damaged ecosystems, and find ways to store carbon or cool cities. It can also strip resources faster than they can be replenished, disrupt climate systems, and create vulnerabilities we didn't have before. The same tools that could keep us among the living could also be the means by which we join the lost. What the graveyard teaches, above all, is that longevity is an active process. No planet stays habitable by accident for billions of years. Even the luckiest start requires ongoing stability in geology, atmosphere and orbital mechanics. For a world with intelligent life, stability also depends on the choices of that life. Choices about how to interact with the planet's systems, how to distribute resources, how to prepare for inevitable disruptions. The moment we stop making those choices with care is the moment the slope toward the graveyard gets steeper. There's another lesson, one that's harder to quantify but no less important. Perspective. Seeing ourselves as one world among many, and as part of a continuum that stretches from lifeless beginnings to inevitable endings, puts our daily concerns in a different light. The problems we face now are urgent, yes, but they are also part of a much larger pattern. The same forces that will one day end Earth's habitability are the forces that shaped it in the first place. The challenge is to make the most of the time in between. It's worth remembering that being among the living is not just a matter of biology, it's also a matter of awareness. We have the rare ability to imagine our own extinction, to recognise the signs of decline, and to think about how to avoid it. That awareness is, in itself, a form of resilience, one that no other species we know of has possessed. It gives us a chance, even if it doesn't give us certainty. And if we fail, then we become part of the story the graveyard tells. Our cities, our satellites, our traces in the geology will be the artifacts future explorers, human or otherwise, will study. They might wonder how long we lasted, what mistakes we made, and whether we ever saw the end coming. They might see us as an outlier, a species that lasted far longer than expected, or as a cautionary tale of one that didn't. In either case, we will join the long chain of worlds that once were alive and are now part of the lost. But we're not there yet. Right now, we're here, breathing the air, walking on the land, looking up at the sky that still protects us. We still have oceans that circulate, forests that grow, ice caps that wax and wane with the seasons. We still have the capacity to act, to adapt, and to imagine futures in which we extend our time among the living. That is a rare position to be in, and it is not one to take lightly. Our place among the lost will come soon enough in cosmic terms. The graveyard is patient. It can wait billions of years if it has to. The question is whether we will reach it because the universe finally makes our world uninhabitable, or because we allowed ourselves to drift into it through neglect, conflict, or inaction. One path is inevitable, the other is not. Which one we take is still within our control, but not forever. So perhaps the most fitting reflection to leave with is this: we are both a survivor and a candidate. A world that has endured against long odds, and a world that could join the silent majority if those odds turn. Knowing that, seeing it clearly, might be the most important knowledge we ever hold. Because only with that knowledge can we decide together whether our place among the lost will come far sooner than it has to, or far later than anyone might expect. And from that decision, everything else will follow, not just for us, but for the story our planet will tell long after we're gone. If you've stayed with me through this journey, thank you for lending your time to think about our fragile, remarkable place in the cosmos. The graveyard of worlds is vast, but for now, we're still here. Let's keep it that way, for as long as we can.